So looking back over this example, basically the task was to load data from this auto MPG. Most of you got through the loading fine. I just quickly want to go through how grouping works and the syntax and the structure and the workflow for grouping data. Starting with the first example, or really, this is the, most of you guys got past part 1. Part 2, some of you guys got stuck on. Compare the data for cars from the year 1970 and 1982. There's more than one way to do it. The most direct approach would be, let me get this in my environment first. The most direct approach, you can either use the describe function, or you can use the basic group by function. So we'll first import it. To my parent directory. And basically, so if I just print this data frame, I've loaded it into memory now. If I just print car data, you can say I have the data frame upon inspection looks good. Everything is in its own column. I'll double check with describe. So really, even just looking at describe, I can see there's some interesting variation. Just looking at the model year, looking at the miles per gallon, there's a reasonably high degree of standard deviation in proportion to the range. One thing I just want to point out quickly is that there's a very useful function in for exploring data that's pd.scattermatrix. If I pass a basic data frame to a scatter matrix, what I'll get, unfortunately it takes sometimes a little longer to execute. What it will do is it will plot every single possible pair. I'll pretty much columns first. By the way, you can squelch output. Sometimes Panda or IPython likes to be very verbose in echoing these sometimes meaningless data to the console. You can squelch that by putting a semicolon at the end. I forgot matplotlib. Import matplotlib. PLT as PLT. I'm just going to import matplotlib. And remember, I have to do inline, matplotlib inline.
What is it?
The matplotlib inline basically allows me to render. What will happen is if I don't have the matplotlib inline, it'll open all my graphs in separate windows. When I declare matplotlib inline, it renders them within my Python notebook. Anything you see whenever you see this % sign in front of the as a first character, that's basically an IPython directive. So this particular syntax is not Python syntax; it is IPython. Run it again. And again, it'll take a couple seconds to crunch all the pairwise visualizations. And it's a little hard to see here. So I can basically just increase the figure size by doing figure size. Let's say equals 16 wide by 16 tall. So this is basically number of points that determines the dimensions of this plot. Rerunning that. You can see, so it's a very quick way to, at a bird's eye view, explore your data. What's interesting is that you can look, if you look at model year, you can see how everything is clearly grouped into these vertical columns. This effect is called banding. You can see banding here. You can see banding here. What causes that banding is that there's, I mean, model year is obviously a discrete variable. Some variables are sort of somewhat discrete. So horsepower, you can see some banding in horsepower, which is kind of interesting. Why would there be this column? This column right here is horsepower, and displacement. You can see clear banding in horsepower and displacement. Why do you think we're getting that banding? Sort of like discretization in those variables.
One's horsepower and the other one what?
This is displacement, which I understand it is.
Horsepower probably changes per year, right? So
It does change. Well, we can look at this graph and determine that, right? So if we look at model year, so this is what you call it's sort of a correspondence. It's basically every variable plotted against itself. If we look at model year as a function of, we can look at model year as a function of horsepower. Horsepower is model year as a function of horsepower. It's sort of like, almost like horsepower becomes less variable over time. It's not necessarily clear that it necessarily goes down. There's a lot of variance early on. So if you go back to, I'll make this a little smaller so it's easier to see at the expense of making it a little less visible. But if you look at, this is model year. So vertical axis is horsepower, horizontal axis is model year. Clearly this is discrete, but interestingly we get horsepower decreases over time, which is sort of interesting. And maybe it's less that it's decreasing; it's just becoming more and more consistent. It's almost as if horsepower, almost as if auto manufacturers are standardizing their process. So I guess they're sort of mass producing their cars in ways that probably gives them less variability here. If you go back to 1970, there's a huge spread in the amount of horsepower that cars have. You have all the way down to 50, all the way up to above 200. Which I guess isn't too surprising. We also see this sort of banding, this sort of grid discretization between acceleration and horsepower. It's not too surprising that as horsepower increases, by the way, acceleration here, I believe it's maybe number of seconds to 60, so a higher horsepower, a lower value in acceleration counterintuitively means a higher force, basically. So, but we're seeing this sort of interesting banding relationship, and sometimes when you have certain variables that are continuous, but they're oftentimes grouped into quantized values. So, if we look here, there's a discrete row of some cars that either in the way they were measured, they were binned all within one single horsepower, and we see that in other trends in the data. So that effect is called banding, and it's just a consequence. Sometimes it's a consequence of how the data was collected. Sometimes it's a consequence of just certain groups of data. So there might be a certain auto manufacturer is standardizing their process, and so all of their cars within a particular model have the same horsepower. And so if that's say like a Honda Civic, then it's going to have the same horsepower across every year, every unit of acceleration. Anyhow, I don't want to go too far into this, but if we look at, let's look at this. We have the car data here. If we do car data, I'll comment all this out for the time being. If we do car data.groupBy, and I'm going to do model year, what we get back is a group by objects. We actually don't get, when we group a data frame, we don't get a data frame back, which seems kind of weird, but it also kind of makes sense. When you're grouping data within a data frame, you're sort of collapsing multiple rows into one. And in order to do that, in order for you to collapse multiple rows into one, you need to apply some sort of operation, you're basically grouping your data. So each one of those groups is itself a population, a subpopulation of your entire data set. So for instance, if I look at print group by model year.mean, what I'm doing is I'm looking at the average of each attribute by model year. So I'm looking at model year 1970, and consistent with the visualization I just showed you, we can see that horsepower is clearly decreasing as model year increases, which is sort of interesting. This result in itself is sufficient some of you asked some details. Like, I mean, we could do stuff like what's the significance of the difference between horsepower as a function of model year? What's, there's certain things like t-tests and population tests, and we'll go over that more at the beginning of this class. The purpose of this exercise is really to familiarize yourself with the group by function. I can do any sort of aggregation function, so group by dot sum, so the total numbers. It makes less sense in this context, but I can add up all the columns. So this is the total sum of all horsepowers of all cars in my data set within the model year. And if I divided that by count, it'd be effectively the same thing as doing the horsepower. So we get the same number here. There's all sorts of things there's all sorts of functions that can be called on group by. But if you want to look at the functions, you can just look at the group by documentation. And there's certain common operations you can do. So mean, there's count, there's sum, etc., etc. So every time you call group by, there's typically a function call after group by. It's like mean or variance or whatever, standard deviation. So you'll see, I just want to sort of clarify that point. Any quick questions on that before we proceed?
So the column that you're grouping by something a list of true and false values. When you do a group by in the column, does it select just where it's true?
Well, how many unique, if you have a column that has both true and false, how many unique values do you have in that column? Yeah, you'll have 2, unless maybe you'll have null. Sometimes you'll have 3 because if you have a null. But the number of unique values in that row that you're grouping is the number of rows you'll have in your result group.
So we'll take the false though as a second value. So
Yes.
them.
No, it will take it basically as being a value. All right. So we're really about a quarter way through the class. The first quarter of the class is slower paced than the rest of the class, which is both good and bad. The good thing is it allows everyone to sort of get up to the same level. Unfortunately, we can't really afford to spend too much time going over the stuff we just went over now about Python and sort of the nuances of syntax and language and things like Git. So a lot of you have been, those of you who have been less familiar with this stuff have reached out to me and Josh and Deepti, and we'll continue to be available as resources for things like resolving Git issues, etc. But the part we're entering now, machine learning, the section of the course here is the course. We talk about data science. It's really where a lot of the when we talk about learning and talking about like gaining insights from data at a quantitative level, typically it's a combination of what we call descriptive analytics, statistics, as well as predictive analytics. So we've talked about what we just talked about at the beginning of this lecture, looking at certain summary statistics on data frames, on data sets. That's what we call descriptive analytics. And we're going to take that a step further and sort of see how we can, given a data set, how can we look at the trends in the data set? How can we infer relationships in the data set so that we can sort of see trends that exist within that data set that hopefully generalize beyond the data set. An example would be we have prices on the stock market and we see very, very clear trends or very, very strong correlations between certain types of stocks and certain growth over time. And so, if we sort of drill down and if we can discover patterns in our data, then if we make the right assumptions and if we are correct and diligent in evaluating our models, we'll be able to generalize and make certain inferences outside of the data set. So future data that we haven't seen yet, this is what we call out-of-sample data, generalized data. And it exists in many forms. So we have the most typical example, most of what we talk about with machine learning is being able to make predictions on observations that have not yet happened. And oftentimes those are future values. Wikipedia gives a very sort of dry definition of machine learning. This is Arthur Samuel. This is back in 1959. He gave a very succinct definition: a field of study that gives computers the ability to learn without being explicitly programmed. Very abstract statement. What does that really mean? What's an example? A field of study that gives computers the ability to learn without being explicitly programmed to do so. Can you give an example of something? I mean, you guys use this stuff all day. In any software you use, any app you use.
Would it be like if you buy something on Amazon and it tells you like recommended items below?
Yeah, that's a perfect example. That's what we call recommender systems, and we'll cover that later in the class. Yeah, so looking at, that's a particular aspect of machine learning that looks at relationships between data. So you have certain behavioral trends. Everyone has certain genres, certain products they like, and it turns out that people tend to sometimes be consistent in the patterns in their consumer behavior. And so what Netflix does, what Amazon does, is they sort of look at that in mass across all the different users, and they see where there's certain commonalities, and they basically try to cluster, try to group, and try to find certain prototypes of users. So you have some users who spend more money, you have some users who like horror movies. They spend money in different ways, but oftentimes there's certain trends. And so if you look at a data set from a high level, you can infer and you can make certain observations that are not obvious, that cannot be done manually without large-scale computation. There's many examples of this and exist in various forms depending on the particular problem we're trying to solve. So, sort of another example, a little more concrete example is, this is sort of an example of where there's some things that are easy for people to do and there's some things that are very difficult for computers to do, and one of them is facial recognition. We can very easily look at a slide like this and tell that what's a face and what's not a face. And we're so good at it that we can, we sometimes see it when it's not even there. It's a fact called pareidolia. When you see a face in the moon, when you see sort of a face in the clouds or whatever, we're so attuned to recognizing certain types of patterns like faces that sometimes we see things when they aren't there. For computers, on the other hand, it's much more difficult because there isn't really a succinct or distinct attribute feature, vector that makes it easier to determine a face from a non-face. So here's some very different examples, very different contrast, perspectives, lighting, and so really there's certain things that computers are very good at doing, like finding relationships and finding patterns in large data sets. There's other things that are much more difficult for computers to do, and this is one such example. But really, what we're trying to do in this example is determine one of two classes. So we have an input. The input here is, we haven't talked about images yet. Although, we've talked about tabular data, we've talked about various representations of data. How would an image be represented as a data set? I guess a better question is, what would the features of an image be?
Pixel values.
Yeah, it's basically just an array of pixel intensities. And so if this image were 256 by 256, then that's a very large, it's 2 to the 16, which is 65,536 total values in a 256 by 256 image. So, this sort of, we have to deal with this massive complexity sometimes where even something very, very simple, like a small image, 256 by 256 is not very large, but when you break it down, it's a tremendous amount of data points to look at when you look at it from the perspective of what that would look like if it were represented in a data frame. This example is what we call a classification algorithm. So the input to the system is an image, a two-dimensional image. The output is a binary classification, whether it's a face or not a face. And so whenever we're outputting a certain type of discrete event, what we call the nominal value in previous lectures, that's what we call a classification algorithm, or classification learner. So there are often times also when the input variables are continuous and the output variables are continuous. We often call that regression. If we're looking for relationships for things like weather, things like stock prices, if we know the trend of weather data at certain points in time, we can extrapolate, we can build regressions, we can build models that describe the relationships between input data and output data. So there's also two distinct, there's sort of two domains in machine learning, two core domains, and that is supervised and unsupervised learning. In supervised learning, we have a large data set that's been labeled, that has already been characterized. And we'd like to take a corpus of data, we'd like to take a large data set, and we'd like to find trends, find patterns, find correlations in that data set that allow us to, as I said before, make predictions about observations we might see outside that data set. This is what we call generalization. And there's always a cost to generalization, because generalization, by definition, when we generalize, we're going outside the bounds of what we know. If I'm talking about finding trends in weather, being able to predict trends in weather based on historical data, then by definition, the very thing that I'm trying to predict is data that I have not yet seen. And there's always a cost to that. There's always an uncertainty. And so when we make predictions, and when we're formulating models that we utilize to make predictions, we have to be careful in how confident we are in those predictions. And in order to do that, we use statistics. And we use a variety of tools that are sort of within the family of what we call hypothesis tests. We can confirm or deny, or we can make an assertion within a certain degree of confidence that our model predicts what it's intended to predict. It's never going to be 100% accurate, but we can say that 95% of the time it will do better than average. And so the more confidence we have, it depends on, there's certain things that where we have very, very strict need to be accurate. In cancer testing, for instance, there's no tolerance for error. In large-scale financial modeling, whenever there's public safety involved, then there's usually a very small margin of error. And so this is something that factors into the choice of algorithm as well. And there's various strategies to deal with trade-offs in managing model complexity with how certain we can be in the predictions we make. Unsupervised learning is a topic we'll sort of cover in the second part of this module of the class. Unsupervised learning is finding relationships in unlabeled data. So in other words, if we're given a large body of data, we want to be able to find certain relationships within that data that we don't already know. So with Kelly's example, she gave an example of how Amazon or Netflix or something like that, a company like that, would find recommend certain products. And if you're looking at a data set, if you're looking at a massive database, if you're looking at Amazon's database, there's various ways you can do that. So we talked about grouping, right? So grouping in a very, very high level sense is sort of almost like forming a sort of classification. We're grouping on forms of discrete data, and we can sort of take that a step further and we can say, well, where are there groups that we haven't yet discovered? Where are there likely to be certain patterns, certain clusters of data, and what strategies can we use to find those patterns, sort of separate the signal from the noise? And there's a variety of algorithms. The class of machine learning algorithms responsible for that are referred to as unsupervised learning algorithms. And we'll give some examples in a bit. So I talked about finding historical data or sort of analyzing historical data in the stock market. Let's say I was looking at every single trade made on the New York Stock Exchange over, say, the last 5 years. I have a massive data set, and I want to take that data set and somehow make some sort of assertion on whether or not the stock market as a whole is going to go up or down. Would that be a form of, would I be doing regression or classification?
Regression.
Sure? My output, the key is my output variable is discrete. It's a finite set. So I'm basically I'm taking a data set and I'm giving a finite set of output values. Either it's going to go up or it's going to go down, assuming it's not going to go completely flat. That's a classification. I'm classifying whether it's positive or negative. If, on the other hand, I said I want to determine by how much it goes up or down, then that's a regression problem. I could say, with a certain degree of confidence that it's going to go up by, I don't know, 100 points tomorrow or whatever. That's a regression algorithm because it's giving me a continuously valued output. And so the type of input that I'm dealing with and the type of output that I want to solve is going to govern the tools and the set of algorithms that are available to me to use to solve that problem. I sort of made this point last lecture that the structure of our data and the type of our data governs what sort of visualizations, what sort of graphs we can plot. And the same thing applies to machine learning algorithms. If I have continuous data, then if my data is continuously valued, the output of my algorithm is continuously valued, then it's not going to be classification. It can't be classification. If, on the other hand, I'm making a determination, like I'm detecting a certain character in handwriting, that's a classification problem. Yeah?
So just like discriminating between classification and a discrete choice. So like for something like if you were predicting a binary outcome and we find that the output says that there's 5.7 times more likely to have this outcome if X and Y. Well, isn't that kind of a combination of a discrete and a sort of classification outcome?
That's a good problem. So I think you're talking about when you have a skewed classifier. So if you're doing something like detecting someone who has cancer and say it's a very, very rare cancer, so 99.9% of your patients aren't going to have cancer. And I could hypothetically have a function that just returns false. And depending on how we determine accuracy, we could say it's 99.9% accurate. But obviously that's not a very good test, right? Because I don't want to be telling people who have cancer, even if there's a 0.1% of them, if there's 0.01% that have cancer, I don't want to be telling that population that they don't have cancer. And so that's what we call sort of a weighted outcome. And there's various strategies of dealing with that. But when we have a skewed, it's still a classifier. But because we have a very skewed set of outputs, we need to weight them, basically apply a penalty, a very, very high penalty for having a false negative. And so that's something that gets factored into the algorithm. And when we talk about, we won't go in depth into classification algorithms today, but there are a variety of strategies for dealing with that. So we'll get into regression a bit more today. I guess I made the mistake of sort of giving away the question with the title of the slide again. But is regression ever going to be unsupervised learning? Why not?
Because you need the data to do the regression.
Yeah, what am I doing? That's a good point, right? What am I doing regression on if I don't have some sort of label with which to score my regression?
You're telling the computer like which variables to compare and they're labeled.
Yeah, in a way with regression I am. So with regression I am taking a set of data and I'm basically trying to find some sort of continuously valued function that fits that data in a way. So if we look at, this is a sort of an artificial example, and maybe not the best example of regression because this probably isn't a great regression, but we can look at what the function of a person's wages is a function of their age. So we have a continuously valued function and we have a set of continuous attributes both in our independent and dependent variable. So we call this, basically this blue line here is trying to describe a relationship between age and wage. And it's sort of interesting, we have these outliers here, way above. Anyhow, this is probably not a very strong regression. And why is that?
Dispersion's pretty high.
Yeah, there's a pretty high variance in my data compared to the data I mean, regression is almost always happy. It'll work. It'll almost always work, but it's not always guaranteed to model reality as well as I hope to. And this is an example when I talk about there's varying degrees of confidence we have in our models depending on really what the data looks like and the methods we choose to analyze that data. And this is a classic example. Again, we can sort of, if we break it down by year, we get again a very, very high spread. So we can represent the data. We can do regression. If we have a data frame, we can do regression independently. So our target variable in this example is what?
Wage.
Yeah, the by target variable I mean the variable that's of interest it's ideally independent of the rest of my data set, and I'm trying to find some relationship between the rest of the variables, the rest of the features of my data, and my output variable, which in this case is wage. If I look at education level, there's also various ways we can represent this data. So we have age, year, and education. Each one of these dots is what? It's a data point, of course, but what is it? What is it really? Like in the real world?
Person.
Yeah. So, I can sort of analyze certain attributes about this person: their age, the year when the survey was taken, their education level, and so forth. So I get there's certain factors that correlate more strongly with their wage and their income, such as education level. So in the example I just showed you, the predictors, there's multiple, unfortunately, oftentimes in nomenclature, because the aspect of machine learning is so interdisciplinary, various disciplines contribute their own sort of vocabulary. And so we often call the predictors, sometimes we call them features, sometimes we call them independent variables, inputs, regressors. Most commonly you'll hear them referred to as features. They're not necessarily always independent, so it's not always fair to call them independent variables, but oftentimes they're referred to as independent variables. And typically we call the independent variables x. This is, I guess, very much like when you go back to high school algebra, you sort of have a plot of x and y, and you typically represent your independent variables on some horizontal axis with y, and the response variable, also known as the target variable, is plotted as a function of some independent variable. Typically in algebra we have a very, very clean and nice continuously valued function. In the real world, when we're looking at data, it's oftentimes dirty, and so there isn't necessarily in fact, there's almost never a very, very clean functional mathematical relationship between x and y. But there can also be times when I have data that's continuously valued in x and y, but is categorical, right? So I can say, let's say tumor size. I want to say if I were to plot tumor size as a function of whether or not that tumor is cancerous, I can say tumor size maybe this is, I don't know, cubic centimeters. And this is false down here. And so as I go up, I have a bunch of observations on various tumors. And tumors can obviously be very small and very large. And maybe I have it's false, and there's like one true, and there's false, and there's false, and there's false, and there's say one true, and there's false. And as I sort of increase with tumor size, I start getting more and more frequent true values. So here it's sort of like in between, and then I start getting more and more true values. And there's a particular, we can use regression to solve these sorts of problems, these discrete problems, but this is ultimately a classification problem. So my classes are true and false. So cancer, malignancy, as a function of tumor size. And you can almost sort of think I could hypothetically fit a line to this, right? I mean, there's no law of mathematics that's prohibiting me from fitting a line to this. But it might not be prudent to do so because the data isn't really linear. And so, this is a particular class of regression we'll look at the lecture after next, and this is called logistic regression. This is a type of regression that we use for classifying data. We use regressive techniques to classify discretely valued outputs. And again, we call each one of these data points, we call these observations. Each one of these is really a tumor, and we call that an observation. In reality, though, for predicting something like cancer, we can often have a lot of descriptive variables that predict, or that can potentially predict an outcome. So, for instance, children born prematurely are at a higher risk of developing infections, many of which are not detected until after the baby is sick. So we want to look at subtle patterns in the data that predict the infection before it occurs. We want to be able to anticipate so that we can incorporate a cure before we make the diagnosis. And so there's a variety of things we might look at: heart rate, respiration rate, blood pressure, et cetera, et cetera. Does having more of these, again, what are these called? Yeah, so these are each features of the data. They're basically variables, columns of my data set that describe, that have some relationship with the variable I'm trying to find, which is whether or not the baby will develop a sickness early in life. Is it better for me to have more of these or more features or less features when doing a classification like this? You seem conflicted.
I mean, I guess you want the right number.
You want the right number. Well, but what is the right number, right? Is there a right number?
Yeah.
I mean, you said that not every single feature is independent. So
That's true. We're going to have some variables that don't correlate at all. We're going to have some variables that correlate with each other. It's actually a little bit easier when the variables don't correlate at all because we can easily remove those. We can say we can use our statistical tests and remove those early on in the data pipeline, the pre-model workflow. And we can use that as a framework to clean our data, is removing columns that we don't need. We've talked about it as being projecting the data to a lower dimension by removing certain columns. But let's say we had a data set where every feature in the data set was independent and had some sort of correlation with our target variable, or some sort of predictive analysis. Is there any cost to having more features?
like computationally,
There's definitely computation issues, yeah. But the more features we have, the more likely we are to the more the data can hurt us if we overfit. And the more ways there are to slice the data. Because the data exists in higher dimensions, and so it often becomes untenable. Oftentimes we can have a good model that doesn't generalize well because there's more dimensions the cost of making a wrong decision on any one of those attributes is going to hurt us. So there's a higher, even though we have more data on which to build our model, we also have more rope to sort of hang ourselves, so to speak, if we act improperly on the wrong feature. If we weight the wrong feature incorrectly, it can very quickly hurt us. So here's sort of an example of a classification algorithm where we have inputs that are continuous, continuously valued. This is the IRIS data set. It's another sort of academic data set. It comes from UC Irvine. The input features are a combination of attributes about the plant. So the Iris setosa, I think, is the Latin name for it. It's a flower and it has various attributes like sepal length, sepal width, petal width, And you can imagine, sort of, if we look at all of these in concert, we can sort of predict or classify the species. And this example, this diagram only shows one, but I think there's 4 total classes, 3 or 4. So if we sort of look at this example in more dimensions, you can imagine we might have a circumstance where say we have 2 types of flower. All right, so I'm just going to, for the sake of making graphing easier, I'm going to look at these 2 columns and the species. And say there's 2 types of species. There's Setosa and Iris. Draw this different color. And as, say, on one axis we have sepal length, and the other axis, say, we have petal width. And again, this is a hypothetical example, but maybe when petal width, when we have we have plants with large petals, but relatively small sepals, you see something that looks like this, where this is again a setosa. We mark that as a circle. And then maybe when I have a sepal length that passes a certain value, then I start noticing that if I have the opposite effect, high sepal length with low petal width, now I start being able to, there seems to be some sort of distinction between my values. And I'd really ideally like to define some sort of margin, some sort of line that separates them. And so again, we talked about functions and values and various ways of defining functions, but this is a classification problem which we can use a form of regression to fit a line between data to draw a distinction between 2 classes or multiple classes of values. Some of these slides I'll sort of come back to later in the lecture, but this is sort of an example of the sepal, or sort of like a classification problem across multiple variables, and predict whether someone will have a heart attack on the basis of demographic, diet, and clinical measurements. So we can see, without even really knowing what the columns are and what the features are in this data set, there's 2 binary, it's a binary classification problem. Red means they have heart disease, blue means that they don't have heart disease. And so, again, is this a supervised or unsupervised algorithm?
Supervised.
Why?
Like,
Yeah, it's already labeled for me. I mean, red and blue, if I didn't have the red and blue labels, if I had to determine the red and blue labels, then it would be a form of unsupervised. But, yeah, I mean, you can see very clearly that there are some attributes, like alcohol, for instance, where, yeah, alcohol seems to have some influence on heart attack. Again, this is strictly from a qualitative perspective. Obesity also seems to have some sort of correlation. Tobacco certainly seems to have some correlation. So we can imagine that when doing a classification, we can extrapolate these features in multiple. This is what we call a multivariate analysis, where there's multiple factors that are influencing the outcome, the predicted outcome of our classifier, of our machine learning classifier. Questions on that? So also OCR, optical character recognition, handwriting recognition, is another example of classification. And again, in this example, the features were very clear. I mean, they were practically plotted for you. But in a data set like this, where say you're working for the IRS and you have 310 million IRS forms to process, or you're doing census data or whatever, and you have a machine that just scans a page and you need to collect this data accurately and classify something like social security number, a zip code, into basically one of the 10 outputs. How would I do this? I mean, we talked about feature vectors here, like certain predictors, but again, what are the features of this data set? What's the dimensionality of each of these? What's the dimensionality of this data set?
Provide as an individual observation.
Each what?
Like each row is an, maybe it's not the present question, but each row is an individual observation, and there's a variance across one outcome across respondents. So it's like understanding if each box was identifying a specific outcome. So for example, column 1 was identifying zeros, understanding where the ink was on that circle and understanding the probability of wherever that.
What do you mean by circle?
So the 0.
Okay. So I mean, if you look at each one of these numbers, you're right that there's a finite set of outcomes, or a finite set of classifications. There's 10 basically. It can be one of these 10 digits. But given this, how do I really? I guess I sort of asked it in the beginning of class, but really each pixel is a feature, isn't it? So even though an image is 2 dimensions in nature, when we think about it in terms of a feature space, it's really, in this case, if this is let's say for the sake of example, that each one of these thumbnails is 8 by 8 or 10 by 10. If it's 10 by 10, then there's 100 features. Even though it's relatively low resolution, that's a pretty high dimensionality to my data set. And so if I'm doing any sort of an image analysis, if I'm doing any sort of it's going to be a tremendous amount of computational overhead to process that many. But are there certain pixels that are more valuable than others?
Yeah.
No? But why not?
Couldn't you infer some of the other pixels based on other pixels, like a general form?
Yeah, I mean, if I look at this, I mean, just sort of eyeballing it, right? It's probably, each one of these, by the way, is, each pixel is continuously valued. Let's say it's 8 bits per pixel, so 256 values, somewhere between completely black and completely white. If I look at all of these, there's certain patterns, aren't there? Like if I look at this pixel, look at this pixel, look at this pixel. If I do the bottom of the pixel anywhere, it's going to always be the same.
The fringes, I guess, are the ones that really are less important.
Yeah, and so, right, so if we sort of look at the corners, if we sort of move towards the center, and we'll probably, what we would see is if we were to weight each of these features in the image, we could almost sort of imagine that if I blew this image up, I can imagine that I can sort of almost score each one of these, and so I can say the dimensionality of each of these images is very, very high. There's a lot of information in my data set, but unfortunately most of that information I don't need. And so I'm going to say basically I can sort of define the mapping in a way, right? So if I sort of break this down, assuming that this, by the way, is just sort of a representation, an abstract representation of the each one of these images. And let's say I want to assign a score to each one of these pixels. And so, you know, if I looked at, just by inspection, I could say most of these numbers have some variance in the center, some don't. By the way, it's not necessarily whether it's white or black. For instance, if I had, say, a pixel that's always black, you know, for instance, like this pixel here is sort of looking across the board. If I look at this pixel right here, it's also black here, it's also black here, it's also black here, it's kind of black here, and so forth. And so it's likely that this also would have, even though it lies on you know, dark value, because it's always the same, there's not much information there. And that's a sort of another thing we're going to look at, is that what parts of our data set give us the most information. And so this value, this pixel here provides low value. This pixel here provides low value. This pixel here provides low value. And sort of these extreme corners provide low value as well. This pixel here provides low value. But as I sort of get more towards the center, if I sort of look at the 0 is kind of different. The 8's kind of similar, but it's kind of not, because it has this one here, and then there's sort of like, there's a lot of variance going on. So as I sort of get around this area of the image, now I say each one of these pixels carries a lot of information with it. Height and so forth. And so when I want to simplify my data set, when I want to make life easier, not just for me, the programmer, but for the machine, and make things more computationally tractable, I might need to say, you know what, I'm just going to remove this. If it's below a certain number, I'm just going to remove it from my data set. I'm going to ignore it. So just like we talked about projection with tabular data, just like we talked about projecting data to lower dimensions by removing columns and named attributes like miles per gallon and car and the assignment you have due on Thursday, the city bike data. There's some attributes that are relevant. There are some attributes that are not. And that's really governed by how much variance there is in each of these in predicting a particular output, and how much they value in each of these data sets. And so, this is, say, if this is 8 by 8, and there's 64, this has 64 features. By the way, I'm going to call this, by convention, to sort of establish the convention, I'm going to call this feature vector x. X is, we could sort of think of it as being two-dimensional or one-dimensional. It would be, so we can sort of unfold this matrix and have a list of these 64 features if we wanted to, right? And so if we were to represent this as a data frame, it would basically look like, I'm going to call this guy x0, x1, and then this guy would be x63. This guy would be, that's this bottom corner. So I would have a very, very wide data frame with my leftmost column being x0, this column being x1, this column being x2, and then this would continue all the way to 63. And what would my rows be? So this is, say, so for instance, x0, I might just remove this column entirely. It's not very useful. By the way, the values here range from 0 to 256. And so this number is going to be between 0 and 256.
So, and
yeah,
you would eliminate that feature based off of low variance.
So looking at my data set, it's always going to be the same, right? So it's basically, in other words, if I looked at this as a data frame, if I sort of mapped out what the value of this top leftmost pixel is, it's always going to be basically 256. In other words, pure white. That's what we call an hexadecimal FFF, or 256, 256, 256 in the RGB color space. But in other words, because this column is always the same, it doesn't really tell me anything, does it? Same goes for this black column, this bottom center attribute here. So I'd probably have, say, like around x128. So maybe this is probably actually closer to, sorry, it's like, this, by the way, is, yeah, sorry, it goes to 63. So this would be somewhere around, I don't know, maybe 50, I don't know. So this would be always sort of approximately 0, approximately 0, approximately 0. And each one of the rows of this data is what again?
It's an observation.
It's an observation, yes. But if I say, what's my target?
No.
So this is, say, 9, this is 8, and I'm just sort of making this up, but this is a classification problem, and this we call our input data, and we commonly denote this as a capital X. X being the matrix that represents our input data. The target variable we denote as Y. Y being the output. It can be continuous, it can be discrete, but I want to establish the nomenclature because it's going to be consistent throughout the class and throughout literature outside this class. So mathematically speaking, Y is in the element of the set of numbers from 1 to, I should start at 0, shouldn't I? From 0, 1, all the way to 9. X is in the element, or I should say xi, yi is in the element of 0 to 255. This should be 255 because it's to the 8. There's 256 values. Starting at 0, that would mean you can go up to 255. So this is a rather meaty example. And again, this form of classification is something we will visit extensively, sort of 2 points down the line. One is when we talk about logistic regression, which is a form of classifier, sort of what I showed here to the left of where we can find a line, if we can find a boundary within our feature space, and we can sort of draw a line to define a boundary between one classification value and another, then we can do classification that way. Another approach is to use what we call support vector machines, which are sort of an extension or extrapolation of this form of classification. So this example is more meaty. It's sort of to introduce the concepts and the nomenclature. If this is confusing, don't worry too much. Again, we'll revisit it. Sometimes it's very worthwhile to sort of plant the seed of the idea in your mind, so it will be familiar going forward. Yeah, just to sort of recap. We went over the given historical market data, determine if the market will go up or down. And you said it was a classification problem. Is it supervised, unsupervised?
Does it depend if you give it labeled or unlabeled data?
Yeah, that's a good point. But I mean, assuming it's stock market data, it's probably going to be labeled, right? I'm going to have access to that. It's not like that isn't, it's public by definition, it's public data. And so, there might be a variety of things I'm looking at. I'm looking at volume traded, looking at price data. There's going to be, stock market data is probably the most complex thing you could analyze. But yeah, I would say it's supervised. And you're right. I think it's actually a valid question that you could, in some ways, think of it as being an unsupervised problem. There's certain trends in the data, certain relationships in the data you could find where you might be able to find relationships or trends. Given historical weather data, predict next week's average temperature. Is it regression or classification?
Regression.
It's definitely regression. Is it supervised or unsupervised? Yeah. Yeah, and again, I mean, there's definitely cases where we sort of explore the data using, unsupervised techniques. And again, sometimes we use, the two are not necessarily mutually exclusive. We can have sometimes what's called semi-supervised, etc. But oftentimes we use, when we're analyzing a data set, we use unsupervised learning as a means to explore the data set and to see certain things in the data that aren't necessarily obvious to the human eye. And this is sort of what we call, there's various methods of doing this called principal component analysis, independent correspondent analysis, but basically looking for where there's patterns in the data. Mathematically, from a mathematical perspective, we can use certain mathematical tools to derive and infer certain relationships in the data that aren't necessarily trivial using fundamental statistical techniques like regression. We talked about these two: determine tomorrow's trading volume and recognize person's face in the image. This is, again, supervised classification, and this would be also regression supervised. So this is a very dense first hour of the class. want to give a few minutes for questions. So again, just to sort of reiterate, these are all topics that we'll be revisiting throughout the class. I just want to basically give you a bird's eye view, and we're going to see certain commonalities, certain trends. But again, the type of algorithm we use is going to govern our strategy for approaching how we solve that problem. And so that's why we sort of introduce these concepts up front and then fill in the gaps as we go along. And we'll start that today using regression. No questions? All right. Give a few more examples of unsupervised learning, and then we'll dive into regression. So yeah, I mean, oftentimes when we do supervised learning, we know the response variable, the target variable that we want to find. We're starting with a specific objective in mind. We don't always have that luxury, though. Sometimes we might want to see patterns in the data, infer trends that we don't yet know. It's one thing if we're starting out with a specific objective. Other times we might be given a very noisy data set or something that's sort of obscure and we don't fully understand it, and we might want to sort of use quantitative techniques to further explore that data such that we can really learn from it. Sort of a historical example was the Rosetta Stone, or certain types of language analysis. So the ancient Egyptian texts were very, very different from any other language, and for a very long time it was almost impossible to. You could see certain patterns, observe certain patterns in the data, but it's very difficult to find any root truth. Or oftentimes you see this in natural language processing and ciphers and so forth, where we can make observations even if we don't know, if we don't have the missing key, so to speak, if we don't have the Rosetta Stone, so to speak, we can at least observe where there's certain relationships between data. We can see where there's commonly used words. We can see where there's articles. We can see where there's a structure within the grammar of the language. And so oftentimes this is used in language analysis and sentiment analysis. If I have a body of text, I might want to see if there's certain words or if there's certain keywords in that body of text that predict, or if they correlate with certain outcomes, or if there's certain words in an email campaign, or if there's certain words in a corpus of review data, there might be certain clusters there that we can mine. So I mean, if we sort of, sometimes we know how many clusters there are, and this is sort of an abstract plot, but if we sort of took the color away in this example, clearly there's sort of 4 central clusters that we can sort of see where there's relationships in the data. Incidentally, and this is sort of a point, but there's actually probably within the City Bike data set that's due on Thursday, there might be some clusters in there that you guys can infer. Maybe not as clear and as distinct as this, but sort of an open objective. You might, in the outcome, you might see certain clusters for how many active users there are, how many registered users there are as a function of time. So try to look for that in your homework. This is sort of a similar example to the City Bike data. Oftentimes we're looking at geographic data, or sort of public data, where there's a lot of disparate variables, and they're a combination of discrete variables, categorical variables, continuous variables, and we want to basically break that down. So how can we look at segments? How do we know, first of all, if we're given a data set, maybe there are, there's always, I guess, sort of this discussion in economics of what differs. Is there a distinct group between the middle class and the upper class and the lower class, or is it sort of all blended together? It sort of brings a semantic meaning to vocabulary. If you can quantitatively describe and say that there is a distinction between certain economic groups or certain cultures, then that speaks a lot louder than the vocabulary that's often used to describe things that are sort of taken for granted at an everyday level with language. So I guess a more concrete example, or sort of a more business example, is, again, in the City Bike data set, you might see certain demographics of users. You might see certain demographics of users that are active. You might see certain trends in the weather data. There might be certain features in the type of weather, whether it's humid or whether it's rainy, and you might be able to identify clusters within that. Any questions thus far?
Sorry. Back to that clustering example, when it says that classify U.S. residential neighborhoods into 67 unique segments, are you starting off by specifying that you are looking for 67 different kinds of, like, I guess, clusters?
That's a very good question. If I don't necessarily know how many clusters I have, how do I? There are times when I know that, and there are times when I don't. And that's actually a very, very difficult thing to do, because you can imagine if I have an algorithm, if I have a way of scoring that algorithm, I can sort of almost have a brute force approach where I try, 100, I try one segment and see how that scores, and I try 2 segments and then see how that scores, and I try 3 segments and see how that scores, and I sort of try to maximize my score that way. And you can imagine that that's, from a computational perspective, extremely cumbersome. It can literally take, even for a supercomputer, can take, if you're splitting these dimensions into multiple dimensions, it becomes exponential and very quickly becomes an intractable solution computationally. So I can use, this is sort of what I talk about, that some algorithms are both supervised, sometimes they're both unsupervised and supervised, where the initial step in analyzing that data is maybe I don't know how many features I have, and I want to use unsupervised learning as a way to cluster and group and find where there's distinct groups within data, so I can break it down and say that there's probably, so I can say maybe there's 67. It's probably not going to be that high in most practical examples. It might be something like 4 or 5 or 6 or 7, and I can sort of like start from there, and I can drill down what the size of my feature space is, or really what the clusters of my feature space look like using unsupervised learning, and I can apply the grouping that we discussed earlier in class. So for instance, an example would be, this is sort of why I brought up banding. Banding is an example when you see those bands in the data, those are sort of groups of data that are related to each other, and sometimes you see that in the plots. This is a very artificial example, but sometimes you see these sort of distinct bands with these certain groups. So if I didn't give you the model year, you might see certain trends where there was, say, like a change in horsepower each year. Maybe you have a car manufacturer that rolls out a new model of car every year, and so maybe the horsepower, the fuel efficiency, or something goes down. And so even if I say I took away that column, the year column, you can use unsupervised learning to infer. Maybe you can use it to both infer columns that you don't know, but you can also use it to reduce the dimensionality of your data set. And that's a very abstract statement, but we sort of saw this in the CARS data set. And we'll go through it in depth when we talk about what's called principal component analysis. But this is a major part of machine learning, is analyzing our data set to see where there are certain clusters or certain inherent groups in the data. And there's we talked about a qualitative way of doing that, but there's quantitative methods for that as well, called principal component analysis and similar methods. So to answer your question, long answer to your short question is it's often a combination of both. We don't necessarily always know what the number of the size of our grouping is. In this case, it was 10. We knew that it was between. We were analyzing a data set where we knew it was between 0 and 9. So there's 10. The total class of outputs is of size 10. But let's say you went to an ancient civilization, sort of taking the Rosetta Stone example, and they used a base 16 numbering system. And by the way, there are civilizations that do have base 6 and base 15, and most commonly it's base 10 because we have 10 digits. But there historically have been cultures that do not use a base 10 system. And so let's say we're looking at a numbering, a scroll that had a numbering system. Could you? You can sort of imagine. You can almost count the number of distinct. You with your eye, you count the number of distinct characters. You can say, well, if there's 16 characters, I have 16 total outputs. There seems to be 16 digits. You can also imagine that each one of these outputs sort of has a signature in a way. And 9 has a certain signature, and 8 has a certain signature. And even if we don't know where that signature is, if we know how to detect that signature, we can sort of map that. We can sort of remap that signature into some feature space, and we can sort of break it apart and drill down that way. And again, these are very abstract concepts, and we'll see these in practice throughout the class. But that's an example where you would need to use both. If you don't know the total number of outputs you have, then you need to use some sort of unsupervised learning technique to drill that down. Does that make sense?
Yeah.
All right. Again, this is sort of a similar example to the last, but if I'm given data on 1,000 medical patients looking at how they respond to certain drugs, and I'm measuring a few things, the effectiveness of the treatment, whether there's side effects, etc., I want to see whether there's certain categories or types of patients in terms of how they respond to the drug. And if so, I want to see what those categories are. Is that supervised or unsupervised?
Unsupervised.
Yeah. Why?
You have no idea how many.
Yeah, I don't know. And again, this is a made-up example, but this does exist in practice. You can imagine the genome, right, where there's certain signatures of genes in the genome, and there's a finite number of genes. There's about 26,000 genes in the human DNA, and you want to do some sort of analysis. But there's about 3 billion base pairs, and most of those base pairs are useless. They don't actually code proteins, but some of those base pairs are. And again, if you were to sort of look at a raw data set of genome data, I mean, it's like looking at binary ones and zeros. There isn't any sense of it. But you can imagine maybe you can find patterns in that data set for certain genes. So maybe there's a certain gene for, and again, genes are always discrete. So we can see the number of genes, and I believe this is how they basically devise and how they find genes in the genome, is that they sort of map it and they try to see where there are certain patterns using an unsupervised learning algorithm. And if you're introducing a drug, that's very relevant because the symptoms of a disease and the symptoms of a drug can manifest as a result of certain genes or certain susceptibilities to symptoms. And again, oftentimes when we're doing clustering, we're discovering something that we don't know. If we were looking at a base 16 system, we wouldn't know when we got the data set that was base 16. We could cluster it and find certain signatures in the data that group to certain feature spaces, and we can cluster those together and infer certain groups of data that we didn't know previously existed. And this is one of those examples. We would have a very similar example to this next example. In farming, given data on crop yields over the past 50 years, learn to predict next year's crop yields. And why not unsupervised?
Well, because you're given your target is labeled, right?
Mm-hmm.
But it's either like crop yield or non-crop yield.
Given data on crop yields, I mean crop yields is really the key word there because that's our target variable. Given crop yields, predict next year's crop yields. So the y, the target variable in this case, would be your crop yields.
So is the input also the predictor?
Well, it's sort of open-ended, right? So we could have a variety of features. I mean, you could probably think about examples of what those might be. We might look at rainfall. We might look at humidity. We might look at like a lot of weather data, right, for agricultural data. It wasn't explicitly specified, but
Yeah, this is not like it doesn't sound like it's asking you to look at other features to predict crop yields. So it sounds like it's saying like, hey, use crop yields to predict crop yields.
that wasn't the intent. But I can see why you're I guess sort of implied in the sentence was that data would include independent variables as well. Because yeah, if you're just looking at crop yields over 50 last years, I mean, you can actually do regression. It's basically like a mean is a type of regression if you think about it. A mean is basically just a regression that's like zero-dimensional in a way. Take a collection of 1,000 essays written on the U.S. economy and find a way to automatically group these essays into a small number of groups of essays that are somehow similar or related. Yeah, this one's pretty obvious. Again, we're just looking at certain features of the data and we're seeing where features overlap. And they naturally group together to form some sort of categorical association. Given historical data of children's ages and heights, predict children's height as a function of their age. Yeah, I think you guys are getting the hang of it by now. It's a supervised algorithm. keyword that we have labeled data here. Ages and heights. Ages, we have their ages and we want to predict their ages.
So if they all regressions are supervised?
Regressions are always, I'm trying to think of a counterexample. Regressions are always supervised. I can't think of an example where you'd use regression without having labeled data. Yeah, regression is always supervised. Other questions? All right. If you open up the, if you pull down the latest from GitHub, in lecture 5, make sure you have the latest. There is a, in the examples folder, let's close all this for now. In the examples folder of the lectures on lecture 6, under exercises, there is a IPython folder called linear regression. That's where we're going to be spending most of the rest of the lecture today, just sort of working through the workflow of how we do linear regression and how we evaluate, how we apply linear regression and how we evaluate linear regression. So I'll give you guys a couple minutes to catch up and open that file. Make sure I can run it. Oh, you're right. I could just lower the resolution, yeah.
Yeah, I have the same problem too, so
They just stash everything, like git stash everything that was like just all their changes just stashes it in like just it. I guess you can I think locally does that. Git stash, stashing it locally, right? Oh, it's Git. You're stashing it in like a Git repository that's not your branch and not the.
No. It's stashed is per repository.
Oh,
You have another Git repository, they're stashed, they're separate.
right.
So you just kind of like push it onto the web, basically.
Yeah, that's kind of what it is.
So is that one like Python?
Because you edit it in class.
Yeah, when you open it, as soon as you open it, it starts autosaving, yeah.
Let's say like I didn't know about Git stash, like to get around it, I've always just used that Python before. And
Yeah, I mean, Git stash is sort of unique too, right? You never Git stash copies, so you lose that word.
So git stash is basically like a separate branch where it basically just pushes all your, it's basically just like a stash. So you do.
You can't pull because they edit the file locally.
Yeah, I recommend that you guys, for the class repository, check out your own branch and do work within your own branch, and that way, when you pull down the master branch, it won't conflict with the changes you've made.
I'd say like make it per lecture branch, so you only keep locally.
Yeah, so that's a good idea.
Check out -b, and then you can do, what's the day, 31st, like 2015 or 331, save it at the end of lecture, being like save lecture 31, and when you need to pull new stuff, you check out master, get pull, and do on on Thursday, you check out -b, a new one. So then you can always go back and look at what work you did during each specific class.
Yeah, so just to really quickly go over this, because I've been getting a lot of questions on this too.
Here,
Oh yeah, sorry. if I make a change to a file, and I do git status, and I see that there's a bunch of changed stuff here. In other words, I have stuff that I've changed. So I've changed things, and if I pull from origin master, then Git has a sort of issue where there's some contention over what it does with my previous work. So if I make a change locally and I do a git pull, it gives you already up to date. But let's say there was something, if I made a change on GitHub, and just for the sake of example, I'll edit the README. And now when I do git pull, it might work. Yeah, so it'll give me your local change to the repository will be overwritten by merge. You guys have all probably seen this. It's a very common but also very benign and easy to fix error. What I can do is I can do git stash, and I'll sort of put this on Slack. If I do git stash and I do git checkout -b, -b stands for a branch, git checkout -branch, I'm going to call this lecture 6. So I have a branch, I'm checking out a branch called lecture 6. So now you can see I've switched from master to the lecture 6 branch. I'm on the same, my history is the same. If I do git stash pop, so I did git stash, which basically pushed the changes I had in my staging area into what's called the stash. It's just a temporary storage area for exactly this purpose. So I have changes that I don't know what to do with. And I switch to lecture 6, I do git stash pop. Now I'm if I do git status, again, I'm exactly where I was previously, but I'm on the lecture 6 branch. And so now I can't switch branches, but I can at least make a commit. Like say this is a temporary commit or whatever. And now if I do git checkout master, and I get this message, your branch is behind origin master by 1 commit and can be fast forwarded. Git pull in this case, I always do a git pull --rebase, git pull -r, which will basically just it'll pull the remote down and plop my latest commit right on top of that. Stash this. Git pull. And again, it's just updated that change, the readme.md. So the keyword really is just to do git stash. And I can say git stash show and see what exists in my stash and what's changed in my stash. This is all in the cheat sheets and on the tutorials I posted on the course resources, so I'm not going to spend too much time going over it now, but I just want to sort of highlight that this is a very common process to do in Git. It's okay if you're getting merge conflicts. It's just Git letting you know that it's not going to throw your changes away.
So you can only you don't stash for a particular branch.
The stash is global.
Stash is just, you're right.
So the stash is sort of almost like, for lack of a better example, like a recycle bin. I can put stuff in it, and it's not going to go anywhere, and I can pull its stuff out. So it's a reversible operation.
So you stick it, you can change branches, and then pull it.
Exactly. Just a temporary area, I can sort of put it in my stash, switch as necessary. So as soon as I stash, within my local directory, it'll go back to all the changes I had on my most recent commit. So it'll basically what's called have a clean working directory. And then once I have a clean working directory, I can pull down changes and I can check out other branches. So looking at sort of what we've covered thus far, we've covered sort of the two different, I guess, classifications of learning algorithms. There's continuous and categorical, and there's supervised and unsupervised. And sometimes, especially with supervised and unsupervised, there's a combination of both or somewhere in between. But all the algorithms we cover, all the machine learning algorithms, to some extent, fit within one of these four quadrants. Regression is an extremely useful and commonly applied technique for, as we mentioned earlier, establishing quantitative relationships between some input data we have and some target variable that we want to predict. We use the example of wages and so on. In this case, we're going to be looking at a more interesting example, looking at specifically advertising data. So far this is pretty routine. I recommend that you not run the examples directly. I'll run the first one because it's, I'm just doing basically the initial setup. But rather than just run these, comment them out and sort of comment inline. It'll just make things, it'll help your learning process if you actually think about and type out and sort of build the muscle memory of what it's like to write this, to go through this process rather than cutting and pasting. So on that note, I have a CSV file on some website. And this is an artificial data set, but it's actually very useful for interesting stuff for regression. Comes from the Introduction to Statistical Learning book. Anyhow, I'll sort of do the initial process, and this is going to be, it might be a bit mundane now, but this is going to be a familiar process of getting data. Data equals pandas pd.read csv URL. And something we haven't seen before is this index call equals 0. And basically, if I look directly at this CSV data, the header data is already in the CSV. So it's just telling pandas, it's being explicit and telling pandas that just look at this first row and infer the column, the feature names from that. This is, by the way, a lot cleaner than the UCI data sets we dealt with, in earlier classes where they had separate name files and so forth. Index call equals 0. This means rows. So if I set index column equals 1, then it would basically be an error because it would try to infer the labels from the row index. I want to infer the labels from the column index, so I'm going to say index call equals 0. And just to make sure I'm the data loaded correctly, I always call data.head to load, just to basically visualize the first 5. Data.head just truncates it non-destructively truncates the data set to the first 5 rows. And again, head is a Unix, it's a Unix convention. So the head command is available within your Unix terminal as well, if you call head. I'll never get to that. Okay. So again, we really have 3. The problem we're trying to solve, our objective is to predict sales based on advertisements in TV, radio, and newspaper. So I guess before I go too far, I think given the previous examples we went over in the slides, it's pretty clear what the features are. But just to be explicit, there's TV, radio, newspaper, and each one of these observations, each one of the values for those observations is an expenditure cost, so it's basically the ad spend on each of those respective channels. By channels, I mean sources, TV, radio, newspaper. And the amount of, basically sales is not in dollars, it's in number of widgets sold. If you don't know, we don't know what we're selling, but again, it can be anything. We'll just call it widgets. So just to make sure, just sort of understand what the dimensionality, or really what the shape, we can call data.shape, and that returns a tuple consisting of the number of rows and the number of columns. So I used head to get the first 5 rows here, but data.shape, just to sort of verify. I always just want to make sure that my data looks as I think it does, and that there's no expected surprises down the road. So I'll call data.shape, and I'll also call data.describe here, just for fun, just sort of see what our summary distributions look like. And again, this is all consistent with what we have here. TV, radio, newspaper sales, there's 200 observations of each. Interestingly, there's some commonalities here. It's sort of difficult to do this without visualizing it. So again, I'll quickly plot the data. one thing we haven't seen before is this sort of subplot syntax. I'll show you what this looks like. I'll sort of go through this one by one. Figure axis, plot PLT. Again, I declared PLT in my imports. That's matplotlib.pyplot. When I call subplots, I'm saying I want a subplot on one row, 3 columns, where they all share the same scale on the y-axis. When we're dealing with matrices, when we're talking about dimensions, note that the first field here is the number of rows, and the second field is the number of columns. And that's consistent with what we got here in shape, right? So in my data frame, I have 200 rows and 4 columns, and this is a consistent format. So that usually when we're talking about addressing a matrix or addressing a data frame, rows are the first index and columns are the second. And I'll do that without doing anything else, and I get this blank plot, which may seem weird at first, but really all I'm doing here with this plt.subplots is I'm defining 2 things. I'm defining fig stands for figure. That's my canvas. So this whole thing is the figure. The axes are each basically the context where the graph gets rendered. Both the axes and the actual context, the space in which the graph gets rendered. If I just do a quick inspection on figure, unexpectedly, every time I call figure, creates a new canvas. And it's sort of this idiosyncratic, it's this weird sort of legacy holdover from MATLAB. There's sometimes we want to plot multiple plots and go back and forth between them. We call fig to create new canvases. I mean, that way we can draw more than one thing at once. It's basically a stateful way in which we can select the certain canvas that we're working with. Yeah.
So what are the first 2 parameters again? It's 1 and 3.
Yeah. So 1 is the number of rows. So subplots gives me multiple plots in a sequence. So everything we've done so far has been 1 plot. That's basically a 1-by-1 cell. Subplots breaks the plot down into 3 cells with 1 row and 3 columns. And I can further see that if I inspect axes, I get an array, and each one of these axes objects is the set of axes for each of these 3. So this is axis 1, axis 2, and axis 3. And oftentimes we'll reference that axis object when we want to do multiple lines on the same plot. We have this data object. Just sort of reiterate, it's this big data frame, 200 observations, and it's a type data frame, and I'm going to call plot. And I'm just going to display a scatter plot. Scatter plot is probably one of the most frequent plots you'll use because it really applies to almost any type of data. I'm going to declare the column that I want to use for my x-axis. So I want to see the relationship between my ad spend on TV, the sales as a function of my ad spend on TV, sales as a function of my ad spend on radio, sales as a function of my ad spend on newspaper. So I'm going to generate 3 separate plots. Each of those plots will describe those relationships. Again, my y-axis for each of those is sales. Note that the string here that I pass here exactly matches that column name. So this string I'm basically using to index the set of observations that make up this data frame. And remember how I talked about we'll be reusing when referencing this axes object. There's a parameter here in plot that lets you specify where you want to render that plot. I'll use Shift-Tab to sort of see what the documentation looks like, and you can see the third action is the axis. And that's just, again, a reference. It's basically a reference to where I want to plot.
So if you had 2 rows of 3 columns each, 4 would be the first one and the second? Like 1, 2,
Yep.
3, 4?
Exactly.
So just doing it in numbers would work.
Yep, it wraps it. So AX, and again, axis 0 is is what? It's the first, I'll get rid of this, I'll run this again to get rid of this data frame. AXS0 is my first set of axes, and that's going to render on this plot. And I'll make it a little larger just to make it a little more visible. And I'm going to say I want the figure size to be 16 units wide and 8 units tall. And sure enough, I get my first plot. So I can see some sort of relationship. Just visually inspecting the data, I can see a relationship between the amount I spend on TV and sales. I'll continue to do that for each of the variables, cutting and pasting this first line. Notice that the figure size, increasing the width, also respectively increase the width of that plot. So it makes it a little bit easier to see. Cut and paste this. Since I've already declared my figure size, I'll keep it simple and keep these out. It's not going to change. The figure size, again, the figure size is the entire canvas. So now that I've set the figure size, unless I change it in each of these subsequent calls, it'll stay stay at that width. And
Is there any way to specify the figure size when you like set the fig and ax tuple?
yes, I believe within subplots there is a way to do it. I believe it's the exact same syntax.
Where is fig being used? Is it like?
It's a keyword. So each one of these is a keyword. I'm not actually declaring a variable. This is just sort of an idiom in Python, is that I can name each of the values that I pass into a function. And so these are what are called named parameters. The reason why named parameters are important is because this function can take a lot of different forms. And so you can imagine if I didn't have to have named functions, I would need to pass an inordinate amount of parameters into this function in order to get it to do anything. There's an absurd number of arguments that this function accepts. And so if I had to basically say pass false or pass all of the defaults, then it would be extremely cumbersome to use. But what I'm seeing here in the documentation, it gives me the definition and it gives me the default values. So in the definition, each of these assignments maps to the default value that function will use if I specify nothing. So it's as if I basically did this and replaced, when I actually explicitly specify my variables, it's as if I'm actually overriding x with TV. So I'm overriding none with my TV axis. I'm overriding y with my with the none axis, etc. And I'm overriding the AX axis, and I'm overriding the fig size axis.
I guess what I'm asking is I see that you're passing in axes, but I don't see that fig being used.
It's not.
It's being used internally within the function's definition, but it's not being internally used. So the scope of fig size, if I call fig size, what sort of, I think where you're confused is, if I call print fig size, I get an error. Fig size is not defined. I'm just associating the value I pass into that function. I'm just binding that association here. So again, if I look at the source for this, just very, very quickly, just sort of illustrate this point. Within, well, I guess you won't quite see it here, but you can see that plot frame it's doing a bunch of delegation here, and this is definitely outside this course, but within this function body, fig size is defined and it is usable within the function because it's declared within the function signature. So here's where it's referencing fig size. So fig size is declared within the function definition. It's not defined outside. And that idiom translates to other, it's not specifically a Python trait. You see that to some extent in Ruby, and you see it to some extent in Java and similar object-oriented languages. And they're called named parameters. So just quickly, I'll plot my other variables, plot my other axes. So let's see, I have radio and I have newspaper. Yep.
I think the question might have been like, instead of setting fig size in a function, could you set a parameter on the fig that you return from subplots?
I think so. The signature in subplots is different. So one of the unfortunate things, one of the trade-offs of having all these separate modules is that they don't always conform to the same interface. They often do, but they don't always. And so sometimes the style, so again, when I call plot on data, this plot is actually defined within pandas. Pandas just delegates that plot to, it just passes that information along to matplotlib. But how pandas does that is slightly different than matplotlib. So subplots, even though it's doing something kind of similar, it doesn't quite have the same function signature. Sometimes you'll see this double star figure keyword, and that's what you call a variable arguments. In other words, I can pass sort of these attributes in a free-form manner. I don't think there is a way to do it within subplots. I could be wrong. I'm not entirely sure. But I don't think it's actually called fig size. I think you actually have to do it. You have to actually do it a bit differently. Maybe I can. Maybe I can. Let's try this. I might eat my own words here. And this is one of the frustrating things, right, is that within the pandas interface, it doesn't specify all of the keywords that it uses. This is just sort of, I guess, life. Pandas is a little bit better at being explicit on what parameters it accepts. But maybe, yeah, name error, fig size is not defined. So no, I can't. Oh, you're right. So likely will work. Yeah, so it looks like I can. So just to sort of illustrate, this should be taller if my assumption is correct. And it is. But we'll make it smaller so it fits on the whole screen. Good question, by the way.
So the first line is matplotlib, and the second line is for all the
So
are from pandas.
it gets kind of complicated because PLT is actually part of pyplot, which is sort of an extension of matplotlib. So if you look up at the signature calls, there's from matplotlib, import pyplot as PLT. Pyplot is sort of like a bundler. It's basically, there's sort of been, with open source, sometimes different groups go different ways, and sometimes there's some changes that are sort of redundant. Anyhow, what PLT is basically an extension of matplotlib. Yeah, it's a module, but it's a pyplot object. Okay. So looking at the data, there's obviously, clearly, a difference in how each of these marketing channels correlates, how much confidence I have in each one of these variables. And again, this is sort of an obvious rhetorical question, but which one looks the best for regression?
TV.
Yeah, TV by a significant. I mean, just qualitatively speaking, newspaper looks like almost like a shotgun blast. Radio looks like something in between, and it's almost like, sort of varying shades of gray here, but TV has a very nice relationship. One thing I'll note, sort of a trend in this data, when we have an increasing variance, you can see how as the cost of expenditure on TV increases, the amount of variance in sales increases as well. And that's what we call heteroscedasticity, a very fancy word for a very simple concept. I'll make a comment of it here, but we'll say the first plot is heteroscedastic. In fact, the second one sort of is too. And it's just a tendency for the variance of a function to increase as its value. It's sort of unfortunate because it gives us a larger spread in our data, but it's a common property in a lot of data is that, as you can imagine, when you're increasing values, oftentimes you're increasing the amount of spread as a function of the expenditure. Questions so far?
Sorry. as you increase the amount you spend on TV, the variance increases, is that what you're
Yeah, so the variance, the spread, it almost looks like a cone. Preferably, I'd like for my variance to stay constant as the value of my independent variable increases. Unfortunately, when I increase an independent variable, sometimes, the noise, if there's a certain degree of noise that's coupled to my independent variable, then when I increase the independent variable, it will scale the noise as well. So imagine this is basically, mathematically speaking, it's some function plus some noise term. So when I scale the value, I'm also scaling the noise term. So if I have basically a function, if I'm trying to fit a function, let's say a line, you can imagine I sort of have this margin here that increases substantially. And what's happening is that y equals some value of x, some function of x, plus some noise term, which is also a function of x. And so when I increase x, actually I should clarify this, that f of x, y is some function of x. So when I increase x, f, the function of x is some scale value of x plus some noise term times a function of x. And when I increase x, I'm not only increasing the value of x linearly, proportionally to x, but I'm also increasing the amount of noise as well. So this x is basically my distribution. It's basically like a Gaussian where the larger this term is, the larger the spread of data I have here. And this is what we call heteroscedasticity.
It's spelling each other.
Another way, in terms of controlling or, somehow normalizing the variance, is there any way that you can do that?
Well, the problem is that the answer is yes, but it gets very, very complicated. And I guess if we can filter that noise, or if we can, early in the data collection process, find a way of minimizing that noise, then that's really the solution. But because the noise is inherently coupled to the input variable, there isn't a way of doing that without destroying information in the original signal. So you can scrub, you can clean noise, but sometimes when you remove noise, you're removing signal as well. And it's a very heavily studied and very theoretical problem that comes up in communications and sensing and signal processing is decoupling noise and filtering noise. And there's a variety of techniques for doing it, but they all have their drawbacks.
So I'm looking at, for example, newspapers. You said it's not a great regression, platform regression, or analyze regression. But isn't it just because it's kind of combined all three to get the sales figures versus, I'm sure if it's just newspapers, money spent on newspapers, and
But what
increase that, you would increase sales. Should there be a better regression line? If you took just newspaper advertising independently.
In a way, that's sort of what I'm doing, right? So I'm doing the plots, each of these plots are independent, so I'm looking at them without any influence of any of the other variables, right? So in other words, if I removed radio, if I took away, again, if I did the projection and I dropped that column from my data frame, I would still have these two plots. If I drop this, I'd still have this one left, and vice versa.
But
So
the sales figure that you're plotting on the y, it's a function of the other two as well. Right?
yeah, it is. That's actually a really good point. Yeah, so that's sort of an example where, we can't necessarily, if we drop a column, then we're dropping that assumption. But if one of them is noise, then it's difficult to, it's sort of like almost like I'm dropping a constant term. If I drew a regression line here, if I dropped radio from TV, but if I drew a regression line sales, it would kind of be here, right? This one is, I guess, less noisy, but there's sort of a regression line here. And so yes, it would subtract, but it would subtract relatively proportionally. And I would lose information, you're right. But because it's not strongly correlated, and this is why we talk about our variables, it's important that our variables be independent of each other. And in this case, they're not. And that's exactly the point you raise, is that when we don't have independence of those variables, we need to have solutions for dealing with that. And we can oftentimes be clever about how we project data and how we remap data to a different space. And that's a common solution for doing that.
I mean, just regarding the general observation about the error term, there are obviously other explanations that are possible as well. I mean, we're limited by the data we have, but for example, you could have if these were sales of winter gear, and so some of the data points were more southern, I don't know, more southern parts of the world, and so fewer people felt the urge to buy a furry cap if they spent more money.
Right.
So it's not necessarily error in the sense of signal to noise per se.
Exactly, that's what we call explained variance, or like things that we can understand the variance of versus unexplained variance, which is essentially our noise.
And would noise have to be sort of evenly distributed if it was true noise?
It would basically, if it were
Like a
true
random
noise,
variable, right?
it would fit a
Random
random variable, specifically a Gaussian. If it was proper random noise, it would,
Right.
via the central limit theorem, it would fit
Yes.
basically a Gaussian. That's a great question. So you can imagine, I mean, that's actually a very relevant example. If we were to basically color, in your example, sort of for the sake of example, if we could color each of these attributes, so maybe there was a group of people that lived in, say we're selling winter gear, right? And so, we might, if we could color each of these examples, and just sort of artificially draw over them because it's not in the data set. But you can imagine that I might see a boundary here where everything above this, I see sort of like this separation, where everything sort of above this line are people that maybe live in the northern part of the United States. And if I'm selling clothes, then I'm probably going to see a higher mode than up here than I am down here. This is, again, what I was talking about, where every time we add a feature to our data set, we're essentially limiting the amount of data that we can cover, right? Because now we need to, because these are distinct, if hypothetically I had to consider each of these differently, now I sort of have to do independent, I have less, and basically every time I split data like that, I'm cutting my data in half. And so let's say I have one variable, I'm looking at north versus south, and because I'm looking at north versus south, or I guess what I'm saying is cold versus slightly warmer, now I've cut my data in half. And let's say I had another variable I don't know, demographics, so I had high income versus low income. Now I have to split my data again, or potentially split my data again. And so every time I introduce a feature, I'm cutting the size or the amount of data that I can analyze in half. And so this logarithmic tendency where I keep cutting the data in half every time I have to slice on an additional column. That's a term called the recursive dimensionality. The higher the dimensionality, I can sometimes fit my data better, but I also have less data with which to fit.
The context of an error term could be different in the sense that error could be error in the standard way, that it's
like measurement noise or
just sort of variation, I don't know. Or there could be another explanatory variable that's not being captured.
Right, but one I can do something with, the other is quite a bit more tricky. If there's actual measurement noise, or if there's if there's sort of sometimes we call this sensor noise. Whenever we're making any sort of measurement, whether it's from a thermometer or from a person, there's going to be some degree of uncertainty, and it's just sort of life. And yeah, the explained, if we can explain what it is, then by definition it isn't noise. And sort of an abstract discussion, but the whole point of noise is that it's a loss of information. Whereas if I have let's say a categorical variable I can split on, then in a way I have more information. I have less samples, but I have more information to split over. So there's a distinction between grouping or seeing where there's certain bands or groups of my data versus noise. All right, so sort of plan a few questions in your head, and then we'll go to break before we cover the rest of the class. But again, this is, you can imagine that this would be a practical example we'd want to solve. We have a lot of money we're spending on various channels. How do we allocate or effectively determine where we allocate our resources? And there's, again, a variety of things that determine that, one of which is how certain we are. So not only the trend in the data, but how confident we are that what we're modeling in the data represents something that we can actually sort of put our money on, literally in this sense. And these are all very high-level questions, but is there a relationship between ads and sales? And qualitatively, we can say, yes, there is. There's clearly some sort of relationship between ads and sales, at least certainly on TV and most likely radio. But we'll talk a little bit later on about how we quantitatively describe that, how we be objective in how we describe how confident we are in analyzing that data. How strong is that relationship? Again, you can imagine that clearly newspaper doesn't seem to have a very strong relationship. And again, clearly newspaper has a lot more noise as well, which is, I guess, just a consequence that it's more difficult to measure newspaper data. I mean, how do you really measure sales based on newspaper? Because with TV, you have Nielsen ratings, and radio, you also have Nielsen ratings, and they're likely to be more accurate. There's a process that Nielsen employs to collect sales and ratings from TV. Newspaper, it's a heck of a lot more difficult. So that determines how strong and how confident we are in that relationship. What ad types contribute to sales? What is the effect of each ad type on sales? And given ad spending in a particular market, can sales be predicted? And these are all sort of similar questions, but we should be able to answer these given the data set. All right, let's take 10 minutes and then we'll get right at it after the break.
I guess Simon, right? The bike, city.
Yeah.
Normalized temperature cells.
They're not actually too clear on this. So I believe what they're doing is perceived temperature, like what you think. For instance, when it's humid, you feel hotter. Like
No, but just the constant normalized temperature in Celsius is divided by 41. So how do I?
I
so
believe
the balance between 0 and 1.
So when you plot data, typically you'll see this a lot where say a bunch of data points here.
Yeah.
Like this. This is what you call normalized data, and it has some mean. So this is y mean, and it has some standard deviation here.
Right.
So we'll call this sigma. Basically what it'll do is it'll basically take y minus each one of these being an observation divided by the standard deviation.
Okay.
This is basically called normalization.
Gotcha.
And it makes the math simpler, and it makes it just a lot easier to solve. Yeah, this is actually also something we call the z-score.
I'll see it. Let's see how.
You deduct the mean from the observations, and then you divide by the system.
Get some.
But they don't give us stats in a way, but so the actual temperatures they can't extract. But
Yeah, I know.
Okay.
That's true.
But just okay, relative. So
if you knew this and you knew the mean, then you would be able to,
But they don't provide it. Okay. So you can't. Gotcha.
I was doing analytics for the first company that I worked for. I didn't call it some logistics engineer. Essentially, I was doing like access data.
How's it going?
So I have two questions. So for the second for some reason, I keep getting this error when I copy paste the data from. Yeah, so I'm getting this here.
Here usually means that you try to reference a column that doesn't exist. Okay. Wait, if you scroll down, it'll give you a little more specifics. Just kind of a little more. Okay, so here, at some point, you tried to reference an array, but it was actually a dictionary.
Okay.
So key error means that you basically tried to access the key in a dictionary that doesn't exist. But same concept applies to a data frame. That's because data frames act like dictionaries. If you try to reference a column by a string that doesn't exist, then it'll give you a key error. So I would check to make sure that your column names that you're passing map what you think there. I think that's probably the issue.
Okay, and then also you're doing the shift tab. It's not working on the computer. Right, to get the information.
That I'm not sure.
Yeah, because we just clicked right there.
Yeah, but well, it has to be at the end of the function declaration, not within, which is kind of annoying. So try putting it at the end of the actual function. And then do a shift tab.
Oh, okay, got it.
Yeah, it has to be within the end or within the
At the end.
yeah, I don't know why. Hey, how are you?
Oh my god, sorry.
Yeah, is that the good stuff?
Yeah, do you have time to help like either now or after class or something?
Yeah. Yeah, we can. I don't know if we have time now, but after class would be probably good.
Thank you.
Sure, no problem.
I have a question for how to plot the data set. So I have a data set, a simple data set, and then I join together, and this is what I get. Oh, sorry. So this is what I get here. So and then I plot this what I get here. Something like this. So but what I really want is, for example, this IGN is split by email site. So here it's like this, but I want to stack this two together into one mesh. So how do I do that?
So I guess I'll draw it to make sure I understand. You have. I'm defining a frame. You want it on a single plot, right?
Right. Yeah.
And you want the bars vertically or horizontally? Okay. And you're trying to plot, what are your variables you're trying to plot, I guess?
So all the process is
Okay, so each one of the bars is basically your
website.
store. Right?
Website. So right now it's all the markers.
Yeah, so it's basically what you call a hierarchical file. Each one is, so you have like your PC Mac, and then what you have. Sure. And then within those, you're trying to basically plot what?
It's channels, for example, deals.
Okay. Yeah, so within those, and are those the same across each of these? Or are they different?
They're the numbers are different.
But the actual fact, the actual
Different. It's actually possible.
so imagine you have email and site, and then
And some other like technology is different channels.
okay, I see. And so each one of these has some sub attribute one, two, three, and then this is say a quantity. Well, first I would transpose the graph. I would plot quantity vertically, and these on the horizontal axis, just for bar graphs, just because it makes the data a little more sense. Because when you talk like bar graphs, I feel like it's usually better if you plot it, unless you run out of space. You probably get rid of space. All else equal, don't look at bar plots on the. Okay, so you did bar horizontal. You did stack. Yeah, so you did dual grouping. I think that makes sense. But I want to see how this
User services, Ruben and I discussed this a lot. We made
I see. So it's like preliminary section. Okay, cool. So you have the column hierarchy. So it looks like your data is being represented properly. Yes, you can use notes and cast. Yeah, so that's what noting does, is that you can reshape and remap those columns. You can, there's also unstack. You can use unstack as well. Unstack is a little simpler.
I want to know what space the number of times
So there's a function called stack. So it's the opposite version of So this is stack. And if you want these to be break the column hierarchy down, so I put those in columns. Does that make sense? Yeah, unfortunately I gotta continue with this stuff. But, okay. Yeah, look at the documentation for unstack and stack. Okay, guys, let's continue. So we have the questions we want to answer. We talked qualitatively about really what we're doing, we're fitting, what we're doing, we're plotting regressions. We haven't really defined what it is quantitatively. And depending on the form of our data, it can get complicated quickly, but it's actually, the basis for a regression is actually relatively simple. I'll sort of illustrate this through example. So I'll take, in the interest of something more manageable than the 1,000 data set graph that we have. Suppose for the sake of example that this is our data set. And I have, let's see, 9 observations. Each one of these, we'll call this our x-axis. And we have a series of xy pairs, and I'll go sort of left to right and sort of map these out, but so like x1, maybe this is, I fill in the axes. So I have x1, 3, 4, let's say 6, let's say 8, let's say 9, let's say 10, we'll say 12, we'll say 14. I'm just sort of representing each of these points on axis. And again, we're sort of, imagine we have tick marks. This maps to say 4. So call this one 1. Call this one 6. Call this one 9. Call this one 5. Let's call this one 12. Let's call this one 11. Call this one. Call this one 6. And call this one 8. Call this one 9. And just to sort of make it more Pythonic, we'll sort of put an index column here. And go 0, 1, 2, 3, 4, 5, 6, 7, 8. So this, I'll call this x0. This is basically a coordinate. And I can call this x0, y0. I can call this one x1, y1, and so on. And this would, I guess, technically be x8. Generalize and say it's x sub n, y sub n. And again, these are just what I defined in my table. My objective, what I need to do is I need to find a line that fits this data. And obviously it already exists here, but this is just a line. It's what we call univariate analysis. It's the simplest type of regression we can do, and so I guess call it regression. So this line is basically defined by two parameters. There's two parameters I can use to define a line. There's a y-intercept, we'll call this beta 0, and there's a slope, I'll call this beta 1. Delta x, delta y. And using these two parameters, again, I can describe any line in the following format. I'll call this line y, I'll put a hat on it to distinguish this line from all the other y's we're using in this equation. Y hat equals beta 1 times x plus beta 0. This is just mx plus b. Same thing you learned high school, whatever, junior high school. It's, if I know beta 1 and beta 0, I know how to define this line. So my objective is to find beta 1 and beta 0. These I call my parameters. And y is what I'm trying to predict. I'm trying to derive a fundamental relationship between my independent variables, whatever those may be. I'm talking in the abstract sense right now. These can be prices. In the example we just showed, it's ad spending dollars, y can be quantity, and so forth. We call this our model. And we want our model to reflect reality as much as possible. And in order for the model to reflect reality as much as possible, it needs to be as close to each of these points as possible, without, in a way, being too close to 1. Again, it's just a line, so you can imagine if we moved it vertically, if we changed the value of b sub 0, we would slightly increase the amount of error, the amount that we're deviating from our model. So again, quantitatively, we want a way to define how good our model is, and we do that through what's called a cost function. And I'll fill this in a second. Given a line, and given a set of data points, I can look at the difference, subtract the value of this observation and my model. Again, this is just an observation, something that exists in real life. Observation, by virtue of being an observation, is something that exists in real life. The model is something that's trying to model real life. It's trying to represent the data so I can hopefully, if I do it properly, generalize this model to data that I have not yet seen. So this is our observation, and this line right here is our model. Again, it's just this y hat equals beta 1 plus beta 0. It's just a line. Given these sets of observations, I'm going to also introduce, I'm going to quantify how far off I was from my observation. And I'm going to do this by introducing a term called epsilon, which is my error term. And you can imagine as I go through each one of these, each epsilon pertains to each observation. So it's almost as if I can add an additional row here and provide some epsilon. Epsilon here is -3. So I'm 3. My model is a few units below. Actually, I'm sorry. We can have this on the second foot. For each one of these, we'll map our epsilon. And this is going to be the difference between y, our observation, and our model is evaluated at that point. Again, y hat sub I is just this value here. Close y1 hat. And I do this for every value of epsilon. So this is actually y sub 0, y sub 0, y sub 1 minus y sub 1 hat. And continue to do that. Do it for each row. And add each one of these up. I'm going to square them, and I'm going to, for each one of these epsilons, I'm going to add it, starting at 0 to n minus 1, at 0 next up, iterate to n minus 1, and I'm going to square it. Why do I square it? Well, there's a couple of reasons. First of all, I want to penalize outliers as much as possible. The error here is high. And I want to penalize errors to a higher proportion than values that are close. There's a drawback to doing that, by the way. The problem is that when I have the squared value, if there's an outlier that's way up here, then it's going to shift my curve a little bit too much. But the benefit of doing the e sub I squared is that, first of all, I always get positive values. So even though that this epsilon is technically negative, this is lower than the projected value. I can, on a more concrete basis, the mathematics, since this is a polynomial, this sum of epsilons is a polynomial, it becomes mathematically simpler to solve. And the derivation for how linear regression is derived and an arbitrary number of dimensions is rather complicated. It's sort of outside the scope of this class. But if this were not a polynomial, I would not be able to analytically derive a closed form solution for this line. And there's a variety of methods that we choose sort of like this to make certain mathematics of the system more simple and more tractable. But again, if I just write this epsilon sub I, just to be more clear, this is, again, just y sub I minus y hat sub I, and I square it. And I call this the sum of squares due to regression. Sum of squares, because it's the sum of squares due to regression. And in order to really evaluate, though obviously the larger, I'm going to call this cost function, by the way. I'm going to call it J. The smaller J is, the better. The smaller J means that my points are closer to the line. I'm summing up over smaller values, so the sum squared residual due to regression is going to be smaller. I call this error, it's also typically called residual because it's what's left over. It's how, when I do the mathematics, it's what I haven't, the difference that I haven't accounted for in my model. It's left over and I still have to account for it through my cost function. The lower J is, the closer my points are. But I could also have a function where the values of y are very large, right? I mean, the scales here could be in the thousands, they could be in the millions, and so I could have values that are very close to my line, but are still very, very large because I've scaled my data, I've scaled my axis so disproportionately that I basically need a way to sort of bring that down to a percentage, or bring that down to a number, hopefully that's normalized between 1 and 0. So what I can also do is I can look at the mean, and I can compare basically how much my points deviate from the mean, compare them how much they deviate from the line. And if I've done my job correctly, if I've done the regression correctly, the points should be closer to the line than they should be the mean, unless it's a constant function. And if it's a constant function, then there's not much point to me doing my regression, because my regression is the exact same thing as my mean, and it hasn't given me much information. But if I've done my job well, and if I have a meaningful model, then the deviation of these points from the mean, and I'll call this mean y hat, the deviation of these points from the mean, sort of draw it up here so it doesn't get too messy, but you can imagine that, again, this is just y minus y mean, and again, this here, and this is reference to the mean, this is y minus y mean. And I do the same thing. And this is y minus y mean. Incidentally, this one is almost square on the average. So the deviation for the mean here is very, very small. And I get an additional function, which is, let's turn the lights up a little bit so you can see my writing. If I sum up the difference of my mean, then I should have something to compare it to. So I use the same approach, and I sum up, it's a terrible sigma. I sum up y sub I minus the mean, and I square it. statistically, what is this similar to? What does this sort of look like?
Variance.
It's variance, it's like variance. It's a non-normalized variance. So if this were variance, if I divided by the degrees of freedom that I have, which is just n minus 1, if I divided by n minus 1, then this would be the variance. And so it's sort of like a scaled variance in a way. And so I'll call this n minus 1 times the sigma of y. And if the ratio of this number to this number, the higher the better. If they're the same, what happens if they're the same? I mean, what happens if my mean, what would it mean if those two values were the same?
No correlation.
It would mean that really I'm not doing any better than, it would be as if basically my regression were flat. It would basically be as if this beta 1 value were 0, right? It would basically just be, my parameter space would just be a beta 0. And if they were the same, this is sometimes called, there's sort of two ways of looking at this, two perspectives. One is the analysis of variance. If my variance of my residuals is the same as the variance of my mean, then I haven't effectively added any information because I haven't actually really found any correlation between, I've done no better than just sort of the average. If on the other hand, this value, if my cost function is significantly less than my variation, then I have something meaningful. And this is quantified through a concept called R squared. And by the way, this is sometimes also called SST. And this is called the sum of the sum squared total. And if I look at SST over R, SSR, if I take 1 and I subtract that ratio, I'm going to call this R squared. If R squared is 0, what does that mean? It'd be as if I took a shotgun blast and if I took a shotgun and I pointed at the board, I just shot a bunch of pellets. I just had basically this spray pattern, right? No matter what regression line I draw through that sort of circular blob of points, isn't going to really be any better than any other line that I draw through that random blob of points. So I can't really gain any information by regression. R squared means that regression isn't doing me any good. If R squared is 1, what does it mean if R squared is 1? By the way, can R squared be larger than 1?
No.
Yeah, probably not. We'll actually see. Well, we'll see examples of what we call an adjusted R squared, which can be larger than 1. One of the problems with R squared is that it tends to make more complex models. It is better. It's closer to 1 the more features I have, which is not necessarily a good thing. And we'll talk about that more in next class. We talk about polynomial regression. But yeah, R squared is going to be bounded between 0 and 1. By the way, also, I mean, I could hypothetically have points that lie along the mean, what would my R squared be if my points lied just straight along the mean? Or were they very close to the mean, right? I'd have a low j, wouldn't I? If this were just a flat horizontal line, I'd have a very small j. I'd have a small j, but what would the sum squared totals be? Wouldn't be 0. Again, the sum squared total, basically, if I flatten my line, it's just the mean, isn't it? It's basically going to, assuming that it's a best fit, again, if I want the line to be best fit, and I deviate from the mean, then I'm basically increasing my cost function. If my line is horizontal and it fits right along the mean, then j is the same thing, the sum squared residual is the same thing as the sum squared total. And again, it's 1 minus 1, so r squared is 0. And mathematically it makes sense, but qualitatively, conceptually, why is my r squared 0 if I have the best fit, even if the line is flat? And we sort of talked about this earlier in class, and it's sort of weird, but the reason why is because I'm not gaining information. It's basically just bobbing up and down, and so what am I really correlating? Well, I'm sort of artificially doing correlation, but there isn't any explained variance. This is what we call the explained variance versus the unexplained variance. And the explained variance here, the amount of difference that I have, the amount of spread that I have in my vertical axis, my y-axis, is explained by my regression. And that explanation comes from the slope of my line. So when my line becomes flat, my variance just becomes noise. I've lost my information, it's gone straight to noise. The variance that I'm getting, my regression, I'm just plotting regression on mean. In other words, I'm just plotting it according to where I'm minimizing variance, but it's still just noise. Make sense? And again, these are sort of heavy concepts, and we'll cover this stuff in a little bit more depth in the next class. But I mentioned also that I want to find beta 1 and beta 0, and I can do that. I'll sort of reveal the formula for doing that. And we'll generalize. The formula we apply works in 2 dimensions, but we'll take that a step further next class and talk about when we want to extrapolate this regression in n dimensions. But beta 1, again, is by definition the change in x over the change in my model. And it turns out, I'm just going to sort of declare by fiat, that that's actually very, very similar to what we plotted here. It's x minus the mean of x squared times y minus the mean of y. Sorry, it's not squared. All divided by the variance in y, which is x minus x bar squared. And again, it's just iterated from 0 to n minus 1. Same thing here, I equals 0 to n minus 1. I also flip this around. And again, if r squared is 0, this number is effectively 0. So it's as if a piece of my puzzle, a piece of my parameter is missing in the case where delta y and where delta y is 0. Beta 0 is trivial to find, provided that I know beta 1. Like I mentioned, I can just solve it here. So I have one unknown left, given that, again, this is a line. So once I know B1, beta 0 becomes my model less my beta 1 times x. Similar to solving 2 equations and doing like a back solve for 2 equations, 2 unknowns. Questions on that? Going back to my example, sort of this was done by the way, is everyone, I'll give it, I guess, a couple seconds. Who still needs time to copy? Anyone? Okay. So, sort of breaking this down into steps, defining our terminology. The sum and the squared residuals, sort of wait for the, this projector sucks, man. This projector's a joke. This I call my cost function. It's sometimes called, it's always, quantitatively speaking, a cost function. It's oftentimes in statistics it's called the sum squared residuals. Other times in machine learning it's usually called a cost function because the larger it is, the more cost, the more penalty we pay for doing our regression. But we ultimately want to minimize that function to the greatest extent possible. And just to sort of reinforce this example, again, different data set, exact same concepts. Right? So what elements are present in the diagram? Well, I'll ask you, so what's beta 1? Yeah, I guess it says it right there. Stats models really, what we haven't covered stats models, and I'm just going to use it this particular lecture for the sake of simplifying the code in this example. Really, what we'll basically look at this and say we get two values here. So this is, we're applying the exact same principle that I showed you an example of on this particular TV data set, right? And we get two values back. It gives us the intercept and the TV. If we refer to this example, what is TV? It's what? Well, the model is sort of the predictor, right? So, but TV, be more specific.
It's about advertising spend.
Yeah, it's actually very, very poorly named in this because it uses, so what I'm doing here is this is called ordinary least squares. The reason we call it least squares is because we're trying to minimize the cost function. So the cost function is squared, and we're trying to get the least squared, and so I guess the natural name is ordinary least squares. And it's called ordinary because there's various ways of doing weighted least squares, and there's various ways of doing that, applying that cost function. But you'll see this a lot. The simplest way of doing a regression is using what's called ordinary least squares. The formula in stats models uses an R syntax. What this is basically saying, this is not a Python syntax, but you can read it from left to right, is sales is a function of TV spend. And maybe I should have named my independent axis better, but TV spend is, again, dollars spent on TV advertising. And that's really all it is. So basically I say, I declare my formula, and I pass in my data. And again, just like in the plotting, the names here, the spelling matters because these map to the columns as defined in my data set. And really, the engine, the work, so this first function call here defines the functions. The fit does the work of finding what beta 1 and beta 0 are. So basically, in the case of univariate analysis, it's just doing this. Not particularly complicated, and we can verify that, although we won't have time in this class. So once I've built my model, I can then extract the parameters from my model, just calling ln params. And yeah, so sort of looking at these questions, how do we interpret the TV coefficient B1? B1 is what? This 0.047. I'll sort of, so you can't cheat. TV means what? if TV was large, what would that mean? Mm-hmm.
Is that the change in sales as a factor of the change in dollars spent on TV?
Yep. And I guess the units, just want to make the units the units are consistent, but yeah, so if this is in dollars, and I guess sales, should have named this axis a little better, but sales is in units. So what this means is that for every time I increase my sales by basically 4.7 cents, I guess I should say, if I divided 1 by this number, it's how many sales I would get by the amount spent. The intercept also, why is the intercept not 0?
You're advertising or not.
Yeah, kind of makes sense. Again, we sort of have to be careful how we interpret things at extreme values. But yeah, I mean, if I spent $0 on advertising, I'd still have some sales. My sales wouldn't be as high, but I would still have some sales. And so the x-intercept, if the x-intercept here were negative, that might call things into question. And so always check the sanity of your values. Always do a sanity check on your regression. If you have values here for intercept and television spend, then it might mean that you have some noise or some outliers to prune, or that maybe there was something wrong with the data. So yeah, every time we spend $1,000, we get an increase in sales of 47.537 widgets. So that's basically this rise over run. Every time we do a certain amount of sales, we increase. Every time we spend a certain amount of money on TV, we increase the number of sales by some fixed amount. Yeah.
Can we see the errors from that calculation?
I don't have a plot here. I mean, I guess I could send it after class, but it would be very, very. It's a little bit dense to see the errors on this plot.
I mean, just the R squared values.
Yeah, we'll see that. We'll see that in a sec. Yeah, so that's actually a good question. So this R squared. So when I plot the function as a function of TV spend, again, what is our red line?
Model.
It's what?
It's our model.
Mm-hmm. It's y hat. But I like the name model better. Sounds better than y hat. And yeah, again, we can see that the model is consistent with the data. It makes sense. It has, a x-intercept, has a y-intercept, and a slope that is consistent with what we observed. And yeah.
Is there a reason the x-axis is starting at -50?
That's just pandas pads it. It will pad a little bit of margin just so it's not plotting. So if it didn't, you can see there's no value below 0. But it just helps visualize the data if there's a little bit of margin on the plot, and so pandas will just sort of pad the plot a little bit, just to make it look nice. And yeah, we sort of talked in my contrived example about confidence in our model. One of the metrics we used, and this is one of the key metrics, is the R squared. R squared is a very simple value. It's good at a high level, but it can also lead to problems because R squared will always do better if I start adding features to my data. As I start making my data set more and more complicated, it scores more and more highly. And I'll sort of visualize it with this data set. Blue is a straight line, obviously. And this is the R squared values, so for each of these respective lines. R squared scores the poorest for blue, and it starts to score higher for green. So again, this is a linear function. Blue is obviously a linear function. Green is a parabolic function, it's a quadratic function. Red is a cubic function. And so as I increase the amount of terms, as I increase the order of my function, as I go from a line to a parabola to a cubic function, my R squared increases. And to an extent, this makes sense. It might be the case that that a cubic function fits the data better. But you can imagine I could sort of keep doing this. I could keep going up like higher and higher order functions. And eventually what I would get is I would get a very, very, very high polynomial that basically just, assuming I went high enough, it could basically almost hit every single one of these points. every time the fundamental law of algebra says the power, the amount of basically the amount of min and maxima in a function, the amount of roots and imaginary roots in a function and repeated roots of a function are the same as the order of that function. So in a parabola, there's either repeated roots, or there's one real and imaginary root in the cubic function. And so each time I add a term, I'm typically adding an additional max and min to that function. And so as I go from a higher order function, I start to overfit the data. And it doesn't happen to me when I'm dealing with linear functions, but when I start having more complex models, then I can start getting a function that has high order and fits the data better, right? So this wavy line, again, is a high order polynomial. It's probably like, I don't know, maybe a 6th or 7th order polynomial. The line is a lot better because it's a lot simpler. But the difference is that you can imagine if I extended this high order polynomial past the bounds of my points, it would go off to extrema very, very quickly. This one would go straight down, this one would go straight up. And as I started to plot points that maybe existed past the range of this initial data set, then I'm start having a very, very high error. And this is what we call generalization error. The data fits the data set that I've given to it very, very well. The higher order, the complex model fits the data very, very well, but it does not generalize to data it has not yet seen because it's too closely fit to the data. It's hugged the data too tightly and it's built too high order of a model, and that's what we call overfitting. And it's not just a problem for regression, it's a problem for almost every type of analysis that we do, and decision trees and so forth. And so it's something that we have to pay attention to and sort of adjust our cost function accordingly to account for the tendency of these algorithms to perfectly fit the data, the data that's given, and not fit the data that it hasn't yet seen. I know this was a pretty dense lecture. We're getting into the fun stuff now. We'll have a lot more on Thursday. So we'll sort of fill this stuff in with Thursday with we're sort of looking at this stuff in higher order. And we'll sort of review hypothesis testing in p-values in a little bit more depth. We sort of set the premise today. I also want to at least introduce a quick concept that I sort of glossed over a bit ago, and that is the concept of multiple linear regression. Again, multiple linear regression is just an extension of what we called univariate analysis. We have a linear function that exists in an arbitrary number of dimensions. And so just like we had a line, so we had one explanatory variable. So we had one feature and one target variable. In the case of the line, as soon as we add another term, you can imagine I can start adding terms here. And every time I add a term to my model, I'm basically going to an additional dimension. So I had, in this example, where I'll have to write it the other way around, where I had beta 0 plus beta 1 times x. Now when I introduce an additional feature, I have an additional beta, I have beta sub 2, and x sub 1. And remember the example we went over in the beginning of class where we had something like 64 in a very, very small 8x8 image? We had 64 of these. And this is two independent variables. Imagine what it looks like when there's 64 of them. It can bring a supercomputer to its knees. But fortunately, there are strategies and ways of dealing with that. But there are certain assumptions, there are certain complications that we have, like we discussed earlier, dealing with linear dependence between variables. And when we go to higher and higher dimensions, it's something we want to avoid. We always want to keep our model as simple as possible. That still explains the data. And having said that, I'll leave it as a class exercise. We'll continue this notebook in next class and go on to polynomial regression. So you have your homework due on Thursday, but I'll leave it open as an exercise for you to review this material, given what you learned in this lecture today, and we'll pick this up on Thursday. Any final questions before you guys have your exit tickets? No? I don't know if that's a good thing or a bad thing. I'll take it as a good thing. Okay, cool. So if you guys could take the last few minutes and fill out your exit tickets, and if there's any other questions, let me know. And otherwise, I will see you on Thursday with your homework on the City Bike data.
So when I'm working with the subplots, say I make this like 2 rows of 4, right? So I'm gonna have 2 rows and like my canvas is gonna be like two rows of plots and 4 in each row. So then when I try to plot this, like I get an error. Is it because like I don't have other plots?
What error does it show you?
So numpy.ndArray object has no attribute get figure.
Scroll up. One more to your back to your code. Do a before comment these 3 function calls out. And call type right after you call the subplots.
Yeah.
Do print type print type AXS. Or sorry, just do print AXS. Okay, so you actually have, so what's happening is that, do you see what's happening?
Well, I'm getting a list, an embedded list. Is it showing me the axes? Or?
Well, what you have there is an array of arrays.
Okay.
And what you had previously when you had 1 rows, you had basically just an array.
Just an array.
Yeah. An array of axes. But now you have an array of axes.
So when I say when I define this parameter here, would I have to set this to because I mean this worked when I had 0, 1, and 2 because I had 3. So in my array I just had like 3 axes, right? So now if I had for this would this say I had like 6, right? Say I had like 2 and 3.
So I was actually mistaken early in class when I said that you could reference it like a 1D array. You have to reference it like a 2D array. What happens is that when you say AXS 0, when you index it with 0, it's not going to return an axis. It's going to return an array. Because you have an array nested within an array, when you say AXS 0, it's going to return you the first innermost array.
Okay.
See what I mean? So if you said AXS 0 and then did the same thing 0, so if you call basically 0, 0, then it will give you the first item in the first list, in the array.
In the array, okay.
Yeah, so basically we have this, right? So sort of simplifying it. We have 1, we have 2. And if I say this is x, if I say x0, I'm going to get back
1.
Yeah, 1 is an array.
Okay.
And so if I were to call, you can imagine what happens if I call x0, 0.
You'll get 1.
Yeah.
Okay.
So I'm just indexing 0, 0.
Okay. So then it has to have, this would have to have more than just one. So if I had like this, I would have to have 0 and say like 4. It would be 0. It would be 1. So to say I'm trying to access this one.
It was 0 indexed, right? So it would be 1 row and 0.
Okay.
Anthony, so when they go ahead and submit the fourth assignment, what are we looking for as an actual in terms of submission? Like, should they submit notebook files and I'll go ahead and open them, or?
Yeah, notebook files.
Okay.
Yeah, I think just
this was at least conceptual for today, right? This is, we didn't even learn the application yet. Really, like how to actually code it. I mean, I want to make sure that I have everything else down pat before I like, really start tackling this.
The coding part is actually really simple. We went through it at the end rather briefly, but yeah.
Yeah, it will.
Oh, when you just like brought in that library or that function in pandas?
Yep.
What was it
It
called?
wasn't. It was in stats models. It was lm.fit basically. The ordinary least squares fit. Yeah. Did it make sense at least? Did you like this part?
I mean, I think the things that I really took away from at least the end of the lecture was, you know, we were talking a lot about like that variance, like that type of, you know.
Explained versus unexplained variance?
Yeah.
Yeah.
I think that was the part that I really took the most out of it.
Really? That's good because that's probably the most difficult to understand.
Really?
Yeah.
Wait.
I think so.
The like variance from the mean versus variance from the model.
Yeah.
Yeah, and then there were like a couple of equations that we take a look at. I mean, that one with 1 minus the variance of the variance of the mean over the variance of the model,
Yep.
right? So that was
The sum squared
sum
total
squared
divided by the
R,
sum squared
sum
result.
T over sum squared R.
Yeah.
I mean, like, those were the things that we kind of did towards the last 30 minutes, right?
Mm-hmm.
Okay.
So basically,
and we're going to go more, we're going to go deeper next class.
yeah, that's like pretty fundamental. So it's not that much. There's a little, yeah. There's deeper concepts, but
That was R squared is equal to
yeah,
that.
yeah. So the cost function is about minimizing
Right,
R squared.
exactly, that's the cost function.
Yeah.
Which is how far away your prediction is from what the actual, how do you even describe that? It's like how much you have to build into your model to like account for like the miss.
The R squared is how closely your line fits the data.
How closely you're like. Okay.
If R squared is 1, it's as if every point is along that line. It's like connect the dots. If it's 0, it's as if you took a shotgun blast and basically if you're doing a regression on a shotgun blast.
And then we also talked about if your line is the mean, then you really don't have any kind of description of like.
Exactly. Even if all your points are constant, yeah, then you're just basically modeling those.
No, that's one thing they didn't understand is because let's say all your points are exactly on the mean. Let's say every single point is on the mean, then you are actually describing that.
But you're not. Remember when we talked about values that don't change, and we talked about the image example I showed? where we're discarding certain columns because they don't give us any information because they're always the same.
Right.
And that's why.
That's right. Okay, fine. So it doesn't give us any description because. Right.
Exactly, it's
But then
useless.
it's impossible to really describe that.
Well, for that feature, yes. If it's constant values, I mean, it's.
So then you would.
I mean, if I give you, like, say, if you're looking at like the digits data, and I give you a column where all the values are the same, and I say, this is x and this is y. So given x, and I say x is 2, 2, 2, 2, 2, 2, 2, and I say y is true, false,
Right.
false, true, whatever, false. And I say predict y given x.
Right.
Yeah.
So you would have to run some. Is there any?
You would need additional information.
You would need
That's my point. Is that there's not sufficient information to solve the problem because there's no change. There's no information.
So my
inherent in the
question
model.
was: is there a different model that you could run, even with that data, that would be able to be a better predictor?
If you could find one, that would be probably one of the biggest discoveries of humankind. Like if you could like take this and like infer this from this, then that'd be amazing.
Okay.
But no, you can't because there's no change. This is we call this like later we get into decision trees. But this is a consistent theme. But yeah, if your independent value doesn't change, then you don't have really.
I mean, because if you did have, let's say, 9 out of 10 were false, and you would be able to predict and say that.
But not very well. If I said, okay, now this one's a 1 and it's true, now you would have some information, but not much. You still wouldn't be able to make a good model. You could say, if it's 1, then it's true, but otherwise, forget about it. This is what we call entropy in information. This is 0 entropy. When we have higher entropy of information, we're trying to maximize entropy in information by maximizing the amount of variance in an independent variable. And that's sort of like what, I mean, it's a different way of stating that.
Cool.
So this, remember this change the segment to yes, right?
Yes. So what's happening is that pandas, by its default behavior, is when you call functions on it, it basically takes the data frame and it duplicates, so it makes a copy of the information. And it does that for a reason. The reason it does that is so you don't accidentally overwrite your information. And so it's giving you that warning, a sort of pseudo-ambiguous warning. It says, because you're calling a function on a function, it's actually just copying the data frame. And so you're actually manipulating the copy rather than manipulating the actual direct reference of the data frame.
Okay. So this is called, here they refer to this as an inline function, is that the term they use?
In order to place these plots properly,
In place. So in place is effectively this.
What are those zeros? What are those references? What is AX? I don't understand.
See, I don't understand the fill in.
So what fill in A is doing is actually, it's sort of an exception to the rule. So fill in A is actually manipulating data. So it actually does directly manipulate the raw data. That's the difference. So fill in A, that's part of the reason why fill in A exists. Is pandas by default doesn't the default behavior is not to
because it was because the thinking behind that is if it's NA, you don't want to do something with it anyway, or
well, it's a common operation, and so if it's NA, it's just a way of it's a common operation, so they provide a means to override the default behavior. That's my interpretation of it.
Okay, but then in this particular example, right? I mean, first of all, I'm not sure it's well written by the author, right? But these look like, well, so this one looks like first it's just saying it's data frame, right? Or declaring that this particular series is from. And then he's using this group by.
So the transform is basically, it's what's cleverly doing the mean.
I just couldn't, I want to know how I can control this.
I believe it's the same thing as calling just mean.
If you wanted to show more than.
Right, and then
yeah.
And then you could. Right. And now you have 6 different factors. 6 representation or 6 different data analysis.
Yeah, and like turn it off, if you turn this to false, then you can, then you'll have like whatever.
I guess I don't
Why?
really understand. I guess I don't really understand the fill NA function well enough.
So the fill NA is all basically just replacing NAs with what you pass to the fill NA function.
Say again?
So if I have a data frame,
Yeah.
And then figure size, like how.
and import pandas is PD, and let's say I have if I have a data frame that looks like this,
So what is 4040?
import numpy as MP, and I do np.na, np.num,
Anyways, you just know that like affects the size of
and basically at a fundamental level it's just
Alright, I'll see you tomorrow. I have to run downstairs for a second.
it's just replacing that number with whatever you pass to it.
See you, Josh. Later.
See it? Sure. So I have one knotted number value in my data frame, and if I do df.fillNA, forget if it's 1 or 2, fill NA with 5, then it just replaces that NA with 5.
Right. Okay, here's what I'm going to, because you recommended I use fill NA, so I'm going to try to rewrite those auto functions using fill NA.
Okay.
You can use fill NA. There's a variety of ways you can do it.
Well, I think that's the problem because it's so flexible. I don't really
There's also, I think,
fill NA with the mean.
I think there's also, yeah, it is. There's a lot of functions in pandas that are like
So you're saying, so I didn't even need to actually do the logical, the logical, whatever you call it,
logical indexing.
Yeah.
Yeah, it makes sense to do it that way, though. You don't necessarily have to, but I think that makes sense.
Right, but I'm saying that I could have just used that.
Well, not necessarily. Yeah, you might be able to. I'd have to sort of rethink about.
Fill an A on column.
Well,
horsepower, right?
you would have it sort of. You could do it with fill an A, but then you'd have to sort of manipulate your whatever you're filling it with to map to properly map to the years. You know what I mean?
Yeah. If there were 6 NAs in the horsepower column,
Yeah.
I could just do whatever we call the data frame. If we only knew there were only 6 NAs in one column,
and you pass an
so
array.
the data frame dot fill NA 0 or fill NA whatever.
Yep.
I could do that, right? I didn't
Yep.
even have to worry about.
Right. And I think fill NA takes an argument that's like in place equals true.
Yeah. What does in place mean?
In place means it does the direct replacement rather than creating what's called a defensive copy. So this is what's called the method of copying the value
As you
of the
mentioned
function.
before.
Yeah, it's a way of protecting internal data from an object from getting corrupted.
Right.
And yeah, that's typically called a defensive copy. And so if I do da.fillNA, I believe, yeah, there's this in place, and so if I say fill NA with 20, I don't know if data has, I don't think it has any NAs, but I do in place equals true, and it will do that in place. And same thing here, if I sort of go back and reset my data frame, fill NA, fill it with 9, and I do in place equals true. Fill NA with
You
9.
already did it.
Yeah, so fill it with 9.
Okay.
Oh, okay.
So in terms of data munging, though, the first step you'd have to do is take whatever represented NA in your data and map it to
You get
NA.
anything out of it?
Well, not that that's necessary. I'm saying that this fill NA looks for explicitly a representation.
It's sort of overloaded in that I believe if you pass it an array, it'll sort of iterate through that array and replace it with those. So if you pass it, see it, if you give it an array, it'll go through each item in the array and it will sort of inject that item, I believe, although I'm not 100% sure on that. But you can imagine I could do, I mean, if I really thought about it, I could do Right, so if I reset this and I say df dot is null, and I do df and I do the logical indexing, right? And I get not do. I'll just index on that column. For the index, was it A? I don't know. It's too late. No, it's this. Oops. This. No. Okay, so if I do dfa dot is null, and I just index data frame on that, and then this is where you're running into problems because you're chaining. It's returning a copy.
Right.
So if I did this, for instance, I don't think it would. Yeah, it'll give me that error. It'll give me that warning because I'm chaining. It's copying a slice from a data frame, and I think I can do it.
So technically, this is a warning now.
Yeah, but it's doing what it's supposed to do. It's just making sure that you know that you're not replacing the original item. So
I'm operating on a copy right now.
Exactly, which is why fill in A is sort of something that's useful.
But you have the same variable name for the copy.
Well, again, internally within this method call is it's making that copy internally within the internal operations of this action. So this returns, I believe, the original reference, but this, because it's a reference of a reference, it returns a copy.
All right.
You can also use like other indexing methods to not have it return a copy.
I got it on more than one occasion outside of that problem too. I mean, is that generally speaking, if you get that, there's a better way to
Not necessarily. It's just being. Pandas is just being explicit, making sure that you're not assuming that you're resetting a value on a data frame. It just make sure that you know that you're updating the value on a copy. But yeah, I would actually probably agree with you that there's usually a better way. If you're doing it that way, then there's usually a better way because there's no reason you should assign to a copy. Because it's sort of pointless.
All right.
That's the biggest problem.
Thank you. No problem.
See you Thursday.
See ya.